language. Okay, yes. Okay, good afternoon, everyone. So this is a AAAI tutorial on pre-trained language representations for text mining. So we have 4 speakers, 4 tutors for this tutorial, all from Computer Science, University of Illinois at Urbana-Champaign. So for this tutorial, I will first just give, because the tutorial is a little long, so I will first give you a little what we plan to do on the the estimated timeline. Okay. For this estimated timeline, what we plan to do is, for the first 15 minutes, I will give a rough or short overall introduction. Then we will have Yumeng to give part 1 on pre-trained language models. Then after that, we'll have Jiaxin Huang give part 2, revisiting text mining fundamentals with pre-trained language models. After this, we plan to have 20 minutes break time. For part 3, after the break, we'll have Yuzhang, Yumeng, and Jiaxin give part 3 on embedding-driven topic discovery. Then part 4 will be done by Yuzhang on weakly supervised text classification, embeddings with less human effort. After this, I will be giving 20 minutes on part 5, advanced text mining applications. Finally, I will give a summary and a future research directions. So that's the whole 4 hours. So for these 4 hours, we plan to have very short break at each time. Not is really break, it's question answering time. That means you have any question regarding to any particular section, we may allow to have 1 or 2 minutes to have a little discussion, a little, like a question answering time. So that's the whole 4-hour tutorial. It's a little long, but hopefully you will enjoy it because the technical contents is rich and it's actually self-explanatory. That means it's quite understandable. Okay. So for this, I will first introduce our 4 speakers. Okay. So the first one is Yumeng. He is currently the PhD candidate at UIUC. He is a recipient of 2021 Google PhD Fellowship on Structured Data and Database Management. This is definitely the highest honor given by Google for the very selected PhD fellowship. Usually 1 year, they only give 1 awardee on 1 recipient on 1 topic like structured data and the database management for whole Americas, sometimes the whole world. Okay. So our second speaker is Jiaxin Huang. She is also a PhD candidate at UIUC. She's a recipient of 2021 Microsoft PhD Fellowship. And for this fellowship, to write on the data or database is also very rare. Usually it's only 1 or 2 winners in the whole field, for whole Microsoft Research Fellowship. Then third one is Yuzhang. She's also a PhD candidate at UIC. She published many, many papers. She's also the recipient of WWW 2018 Best Post-Paper Award, honorable mentioning. Okay. So finally, me, I myself currently serving as Michael Aiken Chair Professor at UIC for among many awards. I probably should mention ACMC KDD Innovation Award in 2004. Okay. So let's start. I probably should switch off this, or I just drag it off, drag it to someplace. Okay, let's start on this one. So the key thing for us to study the text mining, especially for the not for the. Okay, let me see whether I can further reduce it. Okay, so suppose this is the the smallest one we can get exposed on other things. So why we study this pre-trained language model? Simply saying we want to turn unstructured text data into highly structured data. We can do data mining, do machine learning. Why this is so important? Just because over 80% of big data actually are unstructured text data. It's almost anywhere. Okay, that I don't have to give you examples, but if you look at news, research papers, social media, almost anything is unstructured text data. And why it is so complicated? Just because unstructured data is very high dimensional. Okay, without newer methods, if we use the say last 10 years or earlier methods, basically is we just go back to the very high dimension one hot vector. That will not really work, because if you look at two very similar words, they in a very high dimension space, they are very different, as distinct as others. You will not be able to really do interesting semantic analysis. Okay. So that leads to, if we want to mine or analyze such big text data, we have to do something important. One important thing is doing text representation, or we call representation learning. Okay. That's the one for this lecture, mainly we are going to focus on different ways to do it. Then we need to turn the unstructured data into structures. That includes phrase mining, transform unstructured text data into like taxonomy, into structured data, into multi-dimension entities and the relations. Then we can do systematic analysis. Okay. The systematic analysis involves discovering hierarchies, taxonomies, and expand them, exploring text data in a multi-dimensional space. Okay. So let's go down to see why we want to study these pre-trained language models. The first important thing is how we represent text. Like I just mentioned, in the early years, people actually mapped the words into vector space. Okay. That will not work because the vector space, you get a very, very long vector. Okay. Then you get a 10,000 or even more, dimensions. These high dimension leads to meaningful analysis. So the interesting thing is we want to embed them in the lower dimension space. The lower dimension space means you may want to see like those society things or politics things or religion things, they cluster in some nice way. Okay. This nice way actually has been done. If anybody got a common sense knowledge, you probably know in 2013, Google get its word2vec. After that, there are lots and lots of studies on unsupervised word embedding. Okay. Then we are going to introduce those pre-trained language model on this. Another interesting thing is whether this embedding can be supervised or very weakly supervised. Just give you a simple example. If we get, suppose people want to study these 6 names or 6 person. Okay. If you get these people, if we want to see your angle is politics versus science versus literature, likely Richard Feynman and Isaac Newton should be somehow embedded in the closer space. However, if your interest is on England versus United States, you probably want to see like Isaac Newton, William Shakespeare, and Theresa May somehow be embedded closer because they're all from England. So if we see this, we will say to get good embedding, either you say completely unsupervised or weakly supervised could be very, very interesting to provide some assistance for subsequent analysis. Then we are going to introduce the text representations. That means how can we embed those things using pre-trained language model. The language model essentially is you not only take care of each word or each phrase, but you also take out their context. So you take those contexts, you embed the details. I'm not going to introduce here, but you are going to definitely learn besides, word to vec, then you go down to the pre-trained language model, taking care of the context, like a bird or many other things. We are going to discuss this in a more systematic way. And for getting basic structures, one interesting thing is doing phrase mining. Just give you an example, we developed quite a lot of methods and other people as well to turn those unstructured words, combine them into meaningful phrases. Okay. Just this one actually is an example on something like TripAdvisor. Okay, you probably want to see the TripAdvisor. You want to say, something in some dimension. You dig out the phrases. Like this one is about a show. This one is about New York near the High Line. Those collections. You probably can see these things will be much more meaningful, easier to analysis, comparing to just single word. Okay. And another important thing for doing systematic analysis is whether we can do automated name entity recognition and typing. For example, this one is about a coronavirus. If people, of course, people read it, you can understand it, but you want to dig out thousands and thousands of articles to make sense by automated analysis. Okay. So the interesting thing could be, if you look at this, you can say something is a chemical, something is a genome, a gene, something is coronavirus, something is wildlife. You can automatically mark them. Okay. Then you turn this unstructured text data into phrases, into typed entities and the relations. It will facilitate a lot of analysis. The thing can be done automatically with very weak supervision or without supervision, or with just a distant supervision, like some dictionaries or Wikipedia. Whether we can do this, that's a very interesting thing we're going to discuss. Okay. Then once we do this, whether we can turn them into structures, like a multi-dimensional nature of the text. That means we will see you get into like turning this review into like brands, products, aspects, year. So then your analysis of the documents is based on a multi-dimensional space. You can construct text cube also. Okay. Whether we can do automatically get a taxonomy constructed or expanded or enriched. So this one is just showing you for the automatic analysis from the root, we may get into like different fields. For each domain, we may automatically get subdomains or fields we can do analysis. So this is just an example to show this can be done. We're going to cover this as well. Okay. So the whole flow, if you look at this, could be we start from text corpus. We don't want a human to get into massive annotation. We mainly rely on existing knowledge base like Wikipedia. And whether we can do this by using pre-trained language model constructed, lower dimension, but much meaningful, like embedding, clustering, and then we may be able to do text mining, like phrase mining, entity relationship extraction, taxonomy construction, and enrich the topic taxonomy, construct a multi-dimensional text cube, and doing advanced application like text summarization, classification. There are many things can be done. So I'm not going to, in this short introduction, I'm not going to give you the details, but you actually will see every step. We are going to give you newly developed technologies, right, along this domain. Besides, we introduce the general one, we are going to introduce our research groups, also a lot of new methods which publish in the major research venues. Okay, so you probably can see what I can show you is once you can get this multi-dimensional like text cube, you will be able to analyze authors, papers, citations, getting different research fields. You may look at, for example, the trend analysis by different years based on different domains. You look at their papers. Of course, these papers are automatically classified, and you can look at the statistics, including authors' papers. You can do multi-dimensional summarization in a like time, location, or theme, those topic space. So that's the general idea. Then, like I just said, we are going to cover this one by one. I think I have exhausted my 15 minutes. I'm going to pass this down to Yimeng. He's going to introduce part one, which is pre-trained language model. I think the first one, I'm not going to get like a concrete question answering just because it's general philosophy or domain. Once you get into the concrete technical details, they're going to answer your questions as well. Okay, thank you. So I will stop sharing, and Yimeng is going to share using his computer to control the pace. Thank you. So you can share, then you can move on.
Yeah, sure. Okay. Okay, so I believe you can see my screen right now. Okay, hello everyone. This is Yimeng, and I'm from UIUC, a PhD student, and I will be covering the first part of our tutorial on pre-trained language models. And during my presentation, if you have any questions, feel free to type in the chat box, and we will try to answer the questions as fast as we can. And if not, we can reserve a short Q&A session after we finish this part to address the remaining questions. Okay, so let's get started. So in this part, I will be covering a short introduction to text representations, including the context-free embeddings development, and as well as the more recent contextualized embeddings learned by pre-trained language models. Okay, so here is a short brief overview of the development of text representation in the history. So if we want to let machines process text, we have to represent the text into numbers or vectors. So how were texts represented in history? So in early years, we mainly used symbol-based representations, and these include the n-gram model and the bag-of-words models. And in more recent years, we gradually dive into the distributed representations, which have demonstrated much more powerful performance in a wide range of applications. So we first briefly overview the early year symbol-based representations. The general idea of using symbol-based representations is to derive one-to-one correspondence between the text units and the representation elements. So for example, we can use one-hot representations to denote different words. And then in terms of representing documents, we can do bag-of-words representations according to which words are present in those documents. And bag-of-words representation of documents ignores the word order information and only turns the elements to one based on that word's whichever words are present in that document. And we can further weight words with term frequency or inverse document frequency, and this is the so-called TF-IDF weighting scheme. So what is the major issue with these kind of symbol-based representations? There will be many dimensions needed if we want to represent words via these one-hot vectors once we have a very large vocabulary. So this is the so-called curse of dimensionality. And another major issue is that if vectors are represented in this way, these one-hot vectors are equidistant in this vector space, which do not reflect their true semantic similarity between different texts. So next we get into the more recent distributed representations. Very famous distributional hypothesis essentially states that if two words are used or occur in similar contexts, then they tend to purport similar meanings. So when it comes to distributed representations or the so-called embeddings, we're essentially saying that the representation of any text unit should be distributed over all vector dimensions, which means that we are leveraging every vector dimension to represent each word, instead of using the previous sparse 0 or 1 vector representations. And these vectors can be dense and continuous of continuous values. So the major advantage of using distributed representations over sparse representations or symbol-based representations is that we can use turn vectors into dense representations, and they can be lower dimensional even when we have a very large vocabulary. And they are better at capturing semantic similarity. So these distributed representations are usually learned based on the previous distributional hypothesis. So we want the vector space to accurately capture the semantic similarity between different texts. And in this tutorial, we will mainly focus on the distributed representations. And next, we get into the context-free embeddings. So the learning of unsupervised or self-supervised text representations has been one of the most successful early year development of text representation learning in text mining and NLP. The general idea is to map or embed the one-hot vectors previously described in symbol-based representations into a lower dimensional space. So this lower dimensional space essentially becomes the embedding space that captures the semantic information of different texts. And this effectively addresses the curse of dimensionality issue. And there are several favorable properties captured by this word embedding space. So for example, word similarity can be correctly encoded in this embedding space. And also we can derive word analogy relationship by looking at the linear relationship between words in this vector space. For example, we can expect king minus queen to be approximately equal to men minus women in this embedding space. And text embeddings can be used in a lot of downstream applications. For example, if we consider word token or entity level tasks, we can use embeddings for keyword extraction by computing their embedding similarity. We can do taxonomy construction by deriving their parent-children embedding relationships. And we can also use text embeddings in document paragraph level tasks like classification, clustering, retrieval, and also question answering, text summarization, these kind of tasks, which can use those text embeddings as the feature representations for the input sequence. So if we categorize these context-free embeddings, we can, in general, separate them into according to the embedding space they are learned. So the most common ones are learned in the Euclidean space model. And recently there are hyperbolic space model as well as spherical space model that tries to explore non-Euclidean spaces for learning text representations. And we will get into the most common Euclidean space models first. So the most famous Euclidean space model probably is the word-to-vec model. So the so-called Euclidean space essentially means that we do not impose any constraints on the learned vectors. So their vector values can be arbitrary. And word-to-vec is essentially a predictive model which maximizes the probability of observing a word based on the local context. Since similar terms are semantically similar terms usually occur in similar local contexts, we can expect that the learned embeddings, the similar terms embeddings could be embedded closer in this embedding space. And another famous context-free Euclidean space model is called GLOV, which adopts a matrix factorization approach. So basically, we first derive a word context co-occurrence matrix here, which is a sparse and high-dimensional matrix constructed by word counts. And then we want to factorize this high dimensional sparse matrix into lower dimensional word embedding representation matrices. And this is implemented by solving a least squares problem to try to recover the co-occurrence matrix. And then there are developments on further incorporating character n-gram information or features into the embedding learning process. So FastText improves the previous word-to-vec model by introducing this character n-gram extraction approach. So basically, they allow the same subword representations to be shared across different words. So essentially, each word is represented as an aggregation of their character n-grams. And then we get into the hyperbolic space models. So the major motivation of going beyond Euclidean space model is that sometimes the data can have specific structures that can be difficult to capture by a Euclidean space model. And for this hyperbolic space model, the first study is probably this Poincare embedding paper, which explores the Poincare ball model for learning vector representations of entities. So in terms of the hyperbolic space model, we can consider them as the continuous version of trees. And they are naturally equipped to model the hierarchical structures within entities or within tokens. So the reason for this is that if we consider this Poincare ball model, if we are going towards the boundary from the origin of this Poincare ball, the volume of this space essentially exponentially grows exponentially. So basically, we can use this specific characteristic of the model to embed more leaf nodes at the boundary of this Poincare ball model. So basically, when we want to use this Poincare ball embedding model to learn hierarchical relationships, we want to push the general terms like entity to the origin of this Poincare ball, and we want to push the specific words or fine-grained words to the boundary to make them embedded as the leaf nodes. So if we want to consider exploring this hyperbolic space model for text representation learning, a very straightforward approach is to generalize the previous Euclidean space model into the hyperbolic space. And we can easily accomplish this by deriving a hyperbolic counterpart of GLOV. So the major thought is basically use hyperbolic kernels. We can replace the previous Euclidean dot product, which is basically the Euclidean kernel, space kernel of GLOV, into a hyperbolic metric. And then we are essentially learning in the hyperbolic space. And the major advantage of doing so is that there might be some latent hierarchical structure between words. For example, there could be hypernyms, and we can embed them as parent-children nodes in this hyperbolic embedding space. And there are also textual entailment, which might be also represented by these hierarchical relationships. And this Poincare GLOV model can effectively model the generality of and specificity of different terms, as shown in this bottom figures. And finally, we get into the spherical space model. Before introducing the spherical space model, let's consider how we are commonly using text embeddings in applications. So actually, we're mostly using the directional similarity or the cosine similarity between text vectors in the embedding space model. For example, if we want to compute the word similarity between two words, we're essentially computing their cosine similarity in the embedding space. And if we want to perform document clustering, previous studies have shown that if we use spherical clustering algorithms like spherical k-means, we can obtain better performance than Euclidean clustering methods. So basically, we're looking at the vector direction or vector similarity between these text embeddings. So a major issue with the previous Euclidean space models is that there is a gap between the training stage and the usage stage of these Euclidean space models. We are learning embeddings in the Euclidean space, whereas when we want to use them in the applications, we have to do post-processing. We have to normalize these embedding vectors to make them reside on a spherical space. So basically, there is a gap between these two stages. So the inconsistency between training and usage is actually reflected in the objective we are optimizing. So basically, we are when we are learning these text embeddings in Euclidean space models, we are basically optimizing their embedding dot product. But in real applications, we are actually aiming at using their cosine similarities. So basically, the objective we optimize is not really the one we aim. So motivated by this inconsistency, we propose this spherical text embedding model. So basically, we want to close the gap between training and usage. We want to make sure we are learning in the spherical space so that we can directly apply them using their directional similarity or cosine similarity captured during training. So we design a generative model in the spherical space, like how humans write articles. Usually, we will first have a general idea of come up with the general idea we're going to talk about in the paragraph or document, and then we will start to write down each word, and consistent with not only the general meaning, general discourse of the paragraph or document, but also the surrounding words of that center word. So basically, that will formulate a two-step generation process. The first step is that we are generating each center word conditioned on the general meaning of the document or the paragraph. And in the second step, we will generate the surrounding word of that center word based on their vector similarity. So this is a figure of illustrating the process of these generative model. So in the first step, we are generating the center word semantics based on the global context, basically the general meaning we're going to talk about in the document. For example, we can expect images, these kind of words, to be generated from a computer graphics document. And then in the second step, we are generating the surrounding word or the local context of that center word. So you can expect words like gray or display to appear surrounding that center word images. So basically, when we want to train this text embedding model, we will first write out the generation probability and use that as our objective. We want to push the generation probability of the positive sample to be larger than the negative sample over a margin. So this is implemented essentially via a max margin loss. And also, we want to keep in mind that we want to optimize in the spherical space. So we want to constrain the vectors to have unit norms. For this, we utilize the Riemannian optimization. And we also want to incorporate the angular distance in the embedding space. So finally, we can write out our gradient update rule for stochastic optimization. And here are some results of this spherical embedding space model. We first test on word similarity evaluations, and we show that our spherical space model outperforms the previous Euclidean space model and Poincare embeddings model by large margins. And also, we show on document clustering evaluations that the spherical embedding quality is indeed better than the previous Euclidean space models, and regardless of whatever spherical k-means or k-means, these kind of clustering approaches, our embedding method still gives the superior performance. Okay, so now we have finished the introduction of the context-free embeddings, and we are ready to get into the more recent contextualized embedding learning by pre-trained language models. So a major motivation of developing contextualized embeddings instead of sticking to context-free embeddings is that in context-free embeddings, we are essentially using the same or fixed representations for the same word, regardless of the specific context the word appears in. And this could be a problem, especially for polysemists like the word bank. So in the first sentence, open a bank account, and in the second sentence, on the riverbank. Obviously, these two contexts have completely different meanings of the same word bank. But in context-free representations, we are using the same representations for the word bank. And to overcome this problem, we want to learn contextualized word semantics based on the specific context. So here comes the idea of language model training. And in this part, we will first introduce the pre-training of language models and then how to deploy these pre-trained language models in applications. So we have all known that the recent pre-trained fine-tune paradigm have become the prominent practice in a wide variety of text applications. And this pre-trained fine-tune paradigm essentially means that we need to first pre-train a language model. And such pre-training is usually conducted on large-scale general domain corpora. And such pre-training is also unsupervised or self-supervised. Basically, we do not need any annotations, but only learning from the text data themselves. And after pre-training, this language model may have already captured some very generic and generalizable features that can be transferred to task-specific data via fine-tuning. So if we want to categorize the pre-trained language models, they can in general be split into two types. The first type is called unidirectional or autoregressive pre-trained language models. So basically, in unidirectional language models, we are predicting the next token based on all previous tokens. And the unidirectional essentially means that we are leveraging single directional context, basically from left to right. And the representative model under this type is GPT. And the second type of pre-trained language model is the bidirectional ones or autoencoding ones. So in bidirectional language model pre-training, we usually do some masking or corruption of the tokens in the sequences. And then we predict or recover these masked or corrupted tokens using the information in the other original tokens. So this is essentially leveraging the bidirectional context. And some representative pre-trained language models under this type are BERT, XLNet, and Electra. So we first introduced the representative model of unidirectional language model, which is the GPT, standing for generative pre-training. So in unidirectional language modeling, we basically leverage the words that already appeared in the previous, basically the previous words to make the next token prediction. And this is the standard language modeling formulation. To make sure that when we train this transformer and we want to make sure the next token prediction is only conditioned on the previous tokens instead of the subsequent ones, we will apply the unidirectional tension masks. So basically, we do not allow the transformer to attend to the sequence after the target token. And such unidirectional language models can be conveniently used for text generation tasks after pre-training. For example, we can use them for summarization, translation, these kind of new token generation tasks. And these unidirectional language models can be extremely large. For example, the GPT-3 model has hundreds of billions of parameters, and they can be very good at text generation. And they have shown to generate articles that make human evaluators very difficult to distinguish. So if you're interested in the quality of the generated text, you can visit this link for a demo of real articles written by humans versus the model generated text by GPT-2. So we next get into the bidirectional language models. So the previous unidirectional language models only use the previous tokens for predicting the target token. Whereas in bidirectional language models, we want to use both the previous tokens and the subsequent tokens, basically the forward and backward context for making word predictions. Essentially, we are learning representations by combining the two directional contexts. And the first model is ELMO. But ELMO is not a transformer-based model. It's based on bidirectional language, LSTMs. And another issue with ELMO is that it's not deeply bidirectional. It's actually doing independent left to right and right to left context learning using two separate models. And the bidirectional contacts are not used into the very last layer where the two models, the two representations from the left to right and right to left contacts are concatenated. So to make sure we can learn deeply bidirectional contacts, this very famous BERT model proposes a masked language modeling objective. By randomly selecting a subset of words in the sequence and masking them out, the model can learn bidirectional contextualized information to predict the masked words. And BERT has another objective, next sentence prediction, which aims to predict if the second sentence is the subsequent sentence of the first one. And another follow-up work of BERT is ROBERTA. So basically, ROBERTA is proposes several simple modifications to make BERT pre-training more effective, including training the model for longer on more data and removing the next sentence prediction objective, and also applying the dynamic masks across different epochs in pre-training. And another follow-up work of BERT is LBERT, which is a work that focuses on efficient pre-training of BERT model. So basically, they are trying to reduce the parameter space of the BERT model by using lower dimensional token embeddings. So this is so-called factorized embedding parameterization. And also, they allow the parameters to be shared across different layers in the transformer. So essentially, they can use very few parameters to achieve remarkable results. And they also replace the previous next sentence prediction task in BERT into a new sentence level task called sentence order prediction. And next, we introduce another bidirectional language model called XLNet. And XLNet is trying to get rid of the discrepancy between pre-training and fine-tuning, because the previous masked language modeling frameworks introduced the mask token during pre-training, but this mask token is never seen in fine-tuning stage. So XLNet tries to close this gap by proposing this so-called permutation language modeling objective. So in this self-supervised pre-training framework, they randomly permute the text sequences, and then they train the model to predict the target word using the remaining word in the sequence. So basically, if we are randomly permuting the words in the sequence, we are essentially making sure we can access both the forward directional information and the backward directional information to predict the target word. And to realize this permutation language modeling, they devised this two-string self-attention. So why do we need two streams instead of one? This is because if we want to do prediction, when we want to do token prediction, we need to condition this prediction task based on whether the token is serving as the context for other tokens or the token is the target token to be predicted. So if the token is the target token to be predicted, we must not encode the content of the token, basically the identity of the token, into the representation, because that will make the prediction task trivial. But when this token is serving as the context for other tokens, then we must encode the identity of that token, or basically the content of that token, into the representation, so that the other tokens can know what context they are attending to. So basically, they have the content representation, which encode both the token positions as well as the content, to make sure that when other tokens are attending to this token, they have access to the token position as well as the token content. And they have the query representation, which makes sure that when this token is used as the target token to be predicted, the token content is masked out. So next, we introduce another more recent bidirectional pre-trained language model called Electra. And Electra is quite different from the previous masked language modeling frameworks in that it does not use any language modeling objectives. Instead, it proposed a new pre-training task called replace token detection. And this Electra pre-training is implemented using two models, a generator and a discriminator. So the generator is typically a smaller masked language modeling model, and you can consider this generator as a small BERT model. And this generator is trained by predicting the mask tokens in the sequence, as what we have done in BERT. Whereas this discriminator takes the output of the generator as the input. And then the discriminator classifies whether or not each token has been replaced by the generator or the token is original. So why is such a setup more efficient in terms of pre-training? This is because the newly proposed replacement token detection task can utilize all tokens for training, because this is a binary classification task that can be trained on every token. Whereas in mask language modeling training, we can only train the model on the mask tokens, which account for only 15% of the entire sequence. And also we can use a small generator here. So the small generator does not consume that much like training compute. And also we are training the discriminator via the binary classification task, which is simpler than the mask language modeling task, which is a classification over the entire vocabulary. So thanks to this more sample efficient replacement token detection pre-training framework, Electra is able to achieve better NLU natural language understanding performance on the GLUE benchmark than the previous mask language modeling based frameworks. But there are several challenges with this Electra style pre-training framework. The first challenge is that the main model, or the discriminator in Electra, is actually trained using the binary classification task. And this task is much simpler than the language modeling task. So Electra actually lacks the language modeling capability. But this capability is necessary for some setups. For example, in prompt-based fine-tuning, we have to use the language modeling prediction layer to predict the label words. And secondly, this binary classification task may not be fine-grained enough to capture the word-level semantics. And these semantics may be critical for token-level tasks. And another issue with Electra-style pre-training is that the representations from these transformer-based language models often reside in a narrow cone. And this kind of features may raise the risk of degeneration representation. And also this will require the post-adjustment or fine-tuning to derive meaningful sequence representations. To illustrate this issue, we actually provide two plots here. So these plots are basically illustrating the random sequence pairs that are sampling from the pre-training corpus, as well as the semantically similar pairs. And these are sampled from the STSB dataset with the maximum similarity. So we can see that by only using a pre-trained Roberta model or an Electra model, we can actually not meaningfully discriminate basically the random sequence pairs and the similar sequence pairs using the pre-trained embedding space. So motivated by these issues, we proposed a new pre-trained language model called CocoLM. And we have two new pre-training tasks here. The first one is called corrective language modeling, and the second one is sequence contrastive learning. And we are building this model also using an auxiliary transformer as in Electra. So basically, we train this auxiliary transformer as a mask language model, and then use the output of that auxiliary transformer as the input to the main transformer. So in the first task, corrective language modeling, we train the transformer to not only detect the replaced tokens, but also output the original token if the token has been replaced. So basically, we are training this main transformer also using a language modeling framework instead of just the binary classification task. And in the second objective, sequence contrastive learning, we want to make sure that the sequence embeddings are regularized. So basically, the random sequence are separated from the semantically similar sequences. And this is implemented via a contrastive learning framework. And we're using the token replaced sequence and the cropped sequence as the positive pair in contrastive learning, and all the random sequences as the negative pairs. So basically, by formulating such a contrastive learning framework, we can make the sequence representations learned during pre-training robust to both token level and sequence level alterations. And here are our results upon standard fine-tuning of CocoIM model. We have shown that our newly CocoIM model significantly outperformed previous pre-trained language models on GLUE and SQuAD, these kind of common natural language understanding benchmarks. And also, we have a blog post by Microsoft introducing how we scope up this CocoIM pre-trained language model to achieve the state-of-the-art performance on NLU tasks. And we also want to mention this most recent pre-training work on adversarial curriculum, on exploring the adversarial curriculum for language model pre-training. So basically, in this framework, we are using a multi-layer masked language modeling generator to create training signals of different levels of difficulty. We can expect that the training signals generated by the deeper layers are more difficult and the shallow layers to be easier. So by using this multi-layer MLM generator, we can create signals at different levels of difficulty. And then we automatically learn a mixture of this signal generator to provide the most challenging signals for the discriminator for better sample efficiency during pre-training. And this framework will appear in this year's ICLR conference. So we have shown that this new AMOS framework further improves over CocoIM model on GLUE. Okay, so we have introduced several pre-trained language models, and next we will introduce how to deploy them in applications. So the general idea of deploying the pre-trained language models in a specific task is that we want to transfer the generic linguistic features acquired through pre-training to downstream tasks. And there are several usages of pre-trained language models. The first one is the most common one, called fine-tuning, in which we update all parameters in the pre-trained language model's encoder, as well as the task-specific layers. So the task-specific layer in standard fine-tuning is essentially the linear layer that is randomly initialized. And that could also refer to the masked language modeling layer for prompt-based fine-tuning. And the second type of deployment of pre-trained language model is to use parameter efficient tuning. So basically, instead of updating all parameters in the pre-trained language models, we only update a small portion of the parameters. And the third one is prompt-based inference, wherein we do not update any parameters in the pre-trained language models and directly use the language model to make predictions on clause type tasks. So for standard fine-tuning of pre-trained language models, we're adding task-specific layers, usually one or two linear layers that are randomly initialized on top of the contextualized embeddings by the pre-trained language models. And then we jointly fine-tune the task-specific layers and the pre-trained language model parameters. And more recently, there are prompt-based approaches. So basically, instead of adding randomly initialized additional layers, we are reusing the language model layers, basically the MLM head of the Roberta model or BERT model. And then we are converting the task descriptions into the clause questions. And then we ask the language model to predict the label words, which are mapped to the labels. So for example, if we are solving a sentiment classification task, we can concatenate a prompt like it was masked into the input text. And then if the model predicts good or great, this kind of positive semantic word, we will know that this text is basically a positive sentiment text. And otherwise, we can classify this as negative. And these kind of prompt-based approaches have demonstrated much better performance than standard fine-tuning, especially for few-shot settings. And if we want to focus on few-shot fine-tuning and further improve the performance of prompt-based fine-tunings, then we can do some more advanced designs like automatically generating the prompt templates or generating the label words. And also we can do demonstration concatenation by using the training samples to provide hints when we want to do inference for target sequences. And next, we want to also mention and introduce our most recent work on zero-shot fine-tuning. So basically, we have shown that the previous prompt-based approaches have remarkable few-shot fine-tuning performance. But if we directly apply these prompt-based approaches to zero-shot settings, their performance can be significantly worse. And this is because if we do not give any task-specific samples, it's indeed challenging for pre-trained language models to interpret the prompt. So because of this difficulty of doing zero-shot fine-tuning, the current mainstream of zero-shot learning is still based on transfer learning, where we train the pre-trained language model on a large variety of different tasks with abundant annotations. And then we transfer such trained pre-trained language models to unseen tasks. But such a setting will require a lot of cross-task annotations and also sometimes a gigantic model. And these will make these transfer learning-based approaches not practical for common application scenarios. So can we do fully zero-shot learning without using any task-related or cross-task annotations? If we think in this direction, like the humans can create can generate training data pertaining to a specific label when we are given a label descriptive prompt, such as write a negative review, then we can basically believe that the pre-trained language models have the power of creating training data from scratch. So basically, we can leverage the text generation power of pre-trained language models. So in this in our very latest zero-shot learning framework, we employ two types of pre-trained language models, a unidirectional one and a bidirectional one, to create supervision or training data for fine-tuning language models on the generated text. And we call this SuperGen for supervision generation approach. So basically, if we want to do sentiment classification, we can use some prompts like this film is terrible, and then the language model will generate the subsequent tokens, which can be used as the training instance for the label negative. And then if we want to construct sequence pair training samples, we can append some prompts like in other words to make the language models generate paraphrases, intonements, or semantically similar sequences to the previous sequence. So on these 7 glue classification tasks, we can our zero-shot SuperGen model is comparable or even better than strong few-shot methods that use 32 manually annotated training samples per class. So we have introduced this fine-tuning of pre-trained language models, and next we introduce parameter efficient tuning. So instead of updating all parameters in pre-trained language models, we can select to update only a small portion of parameters to make sure our optimization is efficient. So there are a few different strategies for this. The first one is adapter. The second one is prefix tuning, and the third one is low-rank adaptation. So the first one, adapter, is basically trying to add some sub-modules into the pre-trained transformer architecture. So they are added twice to each transformer layer. And they consist of a bottleneck structure, basically is a down project plus an up project. And then when we do tuning, we only update the adapter parameters plus the layer norm parameters and keep all other transformer modules frozen. So basically, we can realize parameter efficient fine-tuning. And the second approach is called prefix tuning. So basically, we want to prepend some trainable vectors to each transformer layer and fix all other vectors. So basically, we're only updating the newly added prefix vectors. And this is similar to how we perform prompt-based fine-tuning, except that in prefix tuning, these prefix vectors are continuous parameters instead of natural language words. And the third type is called low-rank adaptation. So basically, in low-rank adaptation, we want to approximate the parameter update that brings a pre-trained model to a fine-tuned model via some low-rank matrices. So basically, the assumption here is that the fine-tuning of transformers are typically low-rank. So basically, we can use low-rank matrices with far less parameters than full-rank ones to approximate these parameter updates by only training these down project and up project weight updating matrices. And finally, we want to also cover some approaches to use prompts to perform inference directly without any training of further training of pre-trained language models. So basically, we can do some knowledge probing or knowledge extraction from pre-trained language models by devising some clause type patterns or questions. So basically, if we formulate a pattern like a person was born in somewhere or mask, then basically when we ask the language model to predict what are potentially masked tokens, we can extract the factual knowledge from the pre-trained language models that are acquired through pre-training. But there are pros and cons with these kind of pre-trained language models serving as knowledge bases. So the pros is that the language models do not require any schema engineering, and they support open sets of queries. So basically, as long as we can form a natural language prompt, we can use language models to do the job. But there are also drawbacks for this, because the pre-trained language models, the answers from the pre-trained language models are not guaranteed to be accurate compared to a manually created knowledge base. So this basically opens up a unsupervised direction for open domain question answering. And also, we want to mention the strong inference power of large pre-trained language models such as GPT-3. We do not need any parameter updates, but by providing these few-shot training samples as the input to the model, we can guide the language model to generate the correct answer for our target sequence or target questions. So this is basically how the so-called few-shot learning is done in GPT-3. Yeah, I think this is basically the end of this part, and we do have some short time for question and answers. Okay, so maybe I can first answer the questions in the chat box. So the first one is, considering GPT only uses transformers decoder, can we use outputs of GPT as embeddings? I'm not sure if I fully understand this question. So what is the purpose of using, so I'm not sure what is the task or the target of this using the outputs of GPT. Basically, if we want to do text generation, we can directly, okay. So basically, if we are using any transformer-based pre-trained language models, we are essentially learning representations over text. So the difference of using GPT or encoder or decoder-based models is basically how we're going to use those embeddings or transformer representations. So if we are considering text generation tasks, we're only using the decoder-based models. So basically, we're taking the contextualized embeddings of the transformer as the feature, and then add basically a language modeling layer to project that contextualized embedding into real tokens, so that we can predict the next tokens to be generated. So we are always using the the embeddings or representations output by the transformer to do whatever tasks we want to achieve, regardless of the specific architectures we are using for pre-trained language models. So the second one, randomly choosing the layers for fine-tuning, does that imply the layers are created equal? I'm not sure which part is this question referring to, randomly choosing the layers for fine-tuning. I think for parameter efficient tuning, if you are referring to that part, So I don't think we have really done any like randomly chosen of layers for fine tuning. So for fine tuning, we are basically updating all parameters in the model, and only the task specific layers in standard fine tuning is randomly initialized. But the randomly initialized parameters need to be fine tuned to make sure that that layer can produce something meaningful for downstream tasks. And for parameter efficient tuning, we're not randomly choosing the layers. Instead, we are focusing on some specific modules, like in adapters, we are basically tuning the adapter parameters as well as the layer norm parameters. And in prefix tuning, we are basically tuning the prefix vectors. So we're not really like doing some random choices over the fine tuning layers. But if for the question, does that imply the layers are created equal? So basically, only the Albert model allows sharing of like parameters across different transformer layers. So basically, if it's for Albert, we can do the parameters are all tied. So basically, if we are tuning one parameter, one layer parameters, then all other layers will be tuned simultaneously. Okay, so the next one, the first one is in traditional context-free learning, we train using dot product. Okay, but the difference between dot product and cosine is just a normalization. Okay, so the first question is that if we can do like simple normalization of like the vector space models. So the answer is that if we do normalization, we are basically doing a post-processing during our optimization process or embedding learning process. So this is still the same with the previous Euclidean space model if we do not directly optimize in the spherical space. So, so basically we're taking the gradient step following the Euclidean space model, and then we're doing normalization after that. So, so the only difference is how frequent we are doing the post-processing. So if we're doing post-processing if we're doing normalization during optimization, basically we're doing post-processing very frequently during stochastic optimization, but this still leads to the discrepancy or difference between the gap between like optimization objective and usage target. So the only way of turning this or closing this gap is to make sure we directly optimize the cosine similarity in training. So this is essentially our framework, which optimizes in the spherical space. Okay, so the second question is, in prompt-based approach, the automatic prompt generation is referring to sample a prompt from the prompt. Okay, so the automatic prompt generation is actually referring to the second one, generating a totally new prompt in the original paper of that, making language models better few-shot learners. So basically, they're using a T5 model to automatically generate the prompts based on the few-shot samples provided in the training set. Of course, they do provide some like approaches to do some template ensembles. Basically, they can, during inference, they can use different templates and obtain the predictions from different templates and then finally assemble those different predictions to make sure the inference is more stable. And the third one, for pre-trained language tasks, how do I know I collect sufficient large data set? I think this is a good question. So basically, there is always a trade-off or some balance between the data quality and the data size. So in general, the deep learning models have better performance when they are supplied with more like training data, but but you need to make sure that those newly introduced data are not containing noise. So I think the general rule of thumb is that if you have high quality data, then just use those high quality data and then if you know that the other data are low quality or may potentially contain noise, you may be better off using them as unlabeled data instead of labeled data. And there are a bunch of like bootstrapping or data augmentation techniques that we will probably introduce in the next parts of our tutorial to introduce how we can effectively leverage those unlabeled data. Yeah, I think we are a little bit over time for this part. So if you have any further questions, please feel free to type in the chat box and I will continue to answer them in the chat. I think we can proceed to the next part, which will be presented by Jiaxin.
Hi, everyone. Thank you, Imon, for introducing the first part of the tutorial. And I'm going to introduce the second part, revisiting text mining fundamentals with pre-trained language models. So in this part, we will introduce how we will dig into how you use pre-trained language models to solve the text mining fundamental tasks. So similarly, if you have any questions in this part, please feel free to type in the chat box, and later I will type the answers to your questions in the chat box. So in this part, we will mainly focus on 3 fundamental tasks: phrase mining, named entity recognition, and taxonomy construction. So let's first look at phrase mining. So identifying and understanding quality phrases from context is a fundamental task in text mining. Quality phrases refer to informative multi-word sequences that appear consecutively in text, forming a complete semantic unit in certain contexts or the given document. So why do we need phrase mining? So this is because phrases can, a single word cannot represent some complicated concepts like United Airlines or David Dow, but phrases can do. And with phrase mining, there are many important downstream applications in NLP information retrieval and text mining, such as text classification, indexing in search engine, on key phrases for topic modeling or text summarization. So we're going to introduce our framework, UC phrase, which extracts quality phrases in an unsupervised way. Previous phrase mining or chunking models can fall into 2 types. Statistics-based models like top-line seg phrase or autophrase usually use the frequency of phrases, but they sometimes ignore valuable, infrequent, or emerging phrases. Tagging-based models like Spacey and Stanford NLP require expensive and unscalable human annotations for phrases. There are different types of supervisions for phrase mining. For human annotation, they are expensive and hard to scale to larger corpora and new domains. And for distant supervision, they're easier to access, but they tend to produce incomplete labels due to context agnostic matching. For example, we have the complete phrase is heat island effect, but maybe only island effect exists in the distant supervision or the dictionary. And also distant supervision tend to match popular phrases, which form a small seen phrase vocabulary. This makes the model tends to overfit and cannot generalize to unseen phrases. So in our UC phrase framework, we have 2 modules. The first one is silver label generation, and the second one is attention map-based spam prediction. So we will first do core phrases, we'll first mine core phrases as silver labels from documents in an unsupervised way, and then generate sentence attention maps, which will be used to train a lightweight classifier to finally tag the quality phrases. So let's first look into the silver label generation. How do we're inspired by the human ability to accumulate new phrases when reading. Even without any prior knowledge, humans can recognize the consistently used patterns from a document and identify them as phrases. So we want to mine core phrases as silver labels, and our method is to independently mine max word sequential patterns within each document, and then filter out a stop word list. The reason why we do this in each single document as context is because, one, we want to preserve contextual completeness. We want to preserve biomedical data mining rather than data mining. And two, we want to avoid potential noises from propagating to the entire corpus. So here we compare our mined core phrases as silver labels with the distant supervision, such as the Wikipedia titles. We find that core phrases have advantages in both quantity and quality, and preserve better contextual completeness, and they can even find more infrequent phrases in the corpus. For example, our found core phrases can find heat island effect, but if we use wiki entities as distant supervisions, we can only get island effect instead of heat island effect, which is incomplete one. So after we extract the core phrases as silver labels, we want to extract good features for them so that we can train a good classifier. But we cannot directly use traditional embedding-based features. This is because embedding features are word identifiable. It tells you which word you're looking at. So models training on these features can memorize the phrases in the training set easily, and they cannot generalize well to the unseen phrases. We found that the good features for phrase recognition should be agnostic to the word surface names and should reveal the role that the span plays in the entire sentence. That means we want to look at the sentence structure rather than the phrase names. So this is why we need the attention map. We can easily acquire these attention map by inputting the sentence into a pre-trained language model. And this attention map tells us the self-attention between words. So they visualize its inner sentence structure. And this is very critical to phrase classifier, because high quality phrases should have distinct attention patterns from the ordinary spans. So in this example, coal mine and heat island effects are the quality phrases, and others are non-phrases. So given a sentence, we treat all possible n-grams as candidates and select quality phrases from them. And then we convert the problem of phrase tagging into image classification, where the attention map is the input. So then we can train a lightweight two-layer convolutional neural network for binary classification and output whether a candidate is a phrase or not. The reason we use CNN is that it captures word interactions from various ranges and is also fast for training and inference. And also, we don't need to fine-tune the language model for this. So here is the quantitative evaluation of our method UC phrase compared with other method, the supervised method and distantly supervised method. You can see that on knowledge phrase extraction and phrase tagging tasks, UC phrase can outperform the previous methods. And here is also a case study to compare the phrases generated by different phrase tagging methods. And you can see that UC phrase can tag the most complete phrases compared to other methods. So we also looked into another task named entity recognition, which is also a very fundamental task in text mining and information extraction. We will mainly focus on two settings, the few-shot learning setting and the distantly supervised setting. So the task of named entity recognition is a fundamental task in NLP with a wide spectrum of applications, and deep neural models also have achieved enormous success for NER. However, a common bottleneck of training deep learning models is the acquisition of abundant, high-quality human annotations. Notice that every entity in a sequence needs to be labeled. So current NER models are trained for a series of fixed categories using large amounts of labeled data. But when we want to transfer to new domains and categories, we want to learn a few-shot NER models that can generalize well with only a few training examples per type. So we conduct an empirical study on 3 directions to improve the generalization ability of models in limited NER data settings. The first direction is prototype-based methods. We use a training objective that is typically used in few-shot learning setting to represent each class as a prototype, and then minimize the distance between the instance representation and that class prototype. The second direction is noisy supervised pre-training. We mainly let the feature extractor model learn a discriminative NER space by continuously pre-training on a large corpus. And the third direction is self-training. We leverage unlabeled data in the target domain to improve the model after the vanilla fine-tuning. So we will mainly introduce the second and the third directions. So let's first look at the noisy supervised pre-training. Our reasoning is that generic representations via self-supervised pre-trained language models are pre-trained with tasks that randomly masked tasks like randomly masked token prediction. So they treat each token equally and are agnostic to the downstream tasks. However, the goal of NER is to outweigh the representations of named entities. And they want to identify named entities as emphasized tokens and assign labels to them. To smooth the transition between the pre-training stage and the fine-tuning stage on NER, we insert an intermediate stage called noisy supervised pre-training and let the feature extractor model learn a discriminative space for NER. So for this continuous pre-training stage, we use a WeFind dataset. It has automatically annotated NER labels from external knowledge base, free base API. And altogether, it has 113 entity types and over 50 million annotated sentences. Because it is annotated by free base API, there exist noises in the labels. So we call this noisy supervised pre-training. And also it has over 50 million sentences. So it is several orders of magnitude larger than the downstream NER tasks, which makes this pre-training stage robust to the downstream tasks. So we also apply the self-training technique after the vanilla fine-tuning stage. Specifically, we learn a teacher model via cross-entropy loss with labeled tokens, and then generate soft labels using a teacher model on unlabeled tokens. And then we learn a student model via cross-entropy loss on both the labeled tokens and the unlabeled soft predictions by the teacher. So for experiments, we collect 10 benchmark datasets from from various domains. This is because we want to ensure that the various entity types in these domains could not always be covered by the pre-training dataset. And here are the results on the unseen tasks? We have a combination of different, so different columns means different combinations of methods. The LC means linear classifier plus linear classifier attached to a pre-trained language model. The NSB means noisy supervised pre-training. We load a noisy supervised pre-trained model before fine-tuning. The P means we use prototype-based objective for training. And ST means we apply self-training technique after the vanilla fine-tuning stage. And different roles means we have different settings in the experiment. We have five-shot learning, 10% data, and also 100% fully supervised setting. So we have some observations from the experiment results. Firstly, we find that noisy supervised pre-training creates a better discriminative NER space, and they always lead to better results in the data sets. And secondly, prototype-based methods can be better than linear classifier only when the size of both labels and entity types are small. And thirdly, self-training methods that leverage unlabeled data constantly improve the results. We also compared with state-of-the-art NER, a few-shot NER methods. And although IO schema is a defective schema, we empirically find it can lead to higher performance than the BIO schema. But for fair comparison, we report the results of both BIO and IO schemas. And as you can see, our proposed method also consistently outperforms the previous methods on few-shot NERs on all three data sets. So besides few-shot learning setting, we also want to introduce something about distantly supervised setting, where we have distance supervisions, like external knowledge bases or dictionaries for us to refer to. Of course, there can be challenges in distantly supervised NER. They tend to induce incomplete and noisy labels because the distance supervisions or dictionaries are limited, so they have limited coverage of the entity dimensions in the target corpus. And secondly, some entities can be matched to multiple types in the knowledge bases. Such ambiguity cannot be resolved by the context-free matching process. For example, here this figure shows the result of distant label matching. And we can see that directly using the distant labels will result in wrongly labels or incomplete labels. So we cannot directly apply the supervised learning algorithms on these noisy data, because that will lead to overfitting of the models. So we proposed a method called roster, distantly supervised named entity recognition with noise robust learning and language model augmented self-training. So previously we mentioned that if the labels are noisy, we cannot directly apply the supervised training algorithms. This is because we're training with the cross entropy laws, and they can lead to overfitting to the wrongly labeled tokens. So we proposed the generalized cross entropy laws. That means we only use the reliable labels for training the model. Our rationale is that since our loss function is noise robust, the learned model will be dominated by the correct majority in the distant labels instead of quickly overfitting to label noise. If the model prediction disagrees with the given labels from the distant supervision, then that means the labels might be potentially wrong. We also use pre-trained language models to generate contextualized augmentations from the original sentences. So to do this, like in the pre-training stage, we randomly mask out 15% of tokens in the original sequence in the training set. And then we feed the partially masked sequence into another pre-trained Roberta model. And we create augmented sequences by sampling from the MLM output probability for each token. We also apply the self-training technique. The goals of self-training technique are twofold. Firstly, we use the model's high confidence predictions that are likely to be reliable for guiding the model refinement on all tokens. And secondly, we want to encourage the model to generate consistent predictions on original sequences and the augmented ones, based on the principle that a generalizable model should produce similar predictions for similar inputs. So how do we leverage the previously created augmented sequences? So we predict the outputs of the original sequences and the augmented sequences. And we try to minimize the KL divergence between the soft labels of the original ones and the augmented ones. So this way we can leverage the augmented generated sequence. So here are the main results of our method roster. We can find that compared to previous distance supervised method, our method can achieve state-of-the-art on these three benchmark datasets. And we can also achieve close scores compared to the supervised methods. So our final task is taxonomy construction, which is also a fundamental task in text mining. So taxonomy is a hierarchical organization of concepts. And taxonomies can be seen in our daily lives, such as Wikipedia category, medical subject headings, and even Amazon product categories. And taxonomy can benefit a lot of knowledge-rich applications like question answering and knowledge organization. So compared to instance-based taxonomy that only contains one node, or that only contains one word or one token on each node, clustering-based taxonomy has wider semantic coverage and facilitates clearer understanding of concepts. So on each node of the clustering-based taxonomy, there is a coherent topic cluster to comprehend this concept. So in our tutorial, we focus on introducing the clustering-based taxonomy construction. There are several limitations of existing taxonomies. A generic taxonomy with, so generic taxonomies always focus on is-a relation between the parent-child nodes. And also they fail to adapt to user-specific interests in special areas by dominating the hierarchical structure of irrelevant terms. So we propose to construct multifaceted taxonomy. One facet only reflects a certain kind of relation between parent-child nodes. And here are some examples. One relation can be is subfield of, and another relation can be is located in. So there are mainly two stages in constructing a complete taxonomy. The first one is taxonomy construction with minimal user guidance. So in this setting, the users give you a seed taxonomy with in a very small scale. And what you want to do is to output a more complete taxonomy organized by certain relations. And the second one is taxonomy expansion. It updates an already constructed taxonomy by attaching new items to a suitable node on the existing taxonomy. So let's first look at taxonomy construction from scratch with minimal user guidance. So we study the problem of seed-guided topical taxonomy construction, where user give you a seed taxonomy as guidance. For example, here the user gives you the user wants to learn about concepts in the food domain, and he or she gives you a certain seed taxonomy like this. And we want to output a more complete topical taxonomy generated from the text corpus. So this is our example output, and each node is represented by a cluster of terms. So here is our taxonomy construction framework, Coral. So it has 3 steps. In step 1, it learns so from the user given seed taxonomy and an in-domain corpus, it learns a relation classifier and transfer the relation upwards to discover common root concepts of existing topics. And then in the second step, it then transfers the relation downwards to find new topics and new subtopics. And in step 3, it then expand each node to form a coherent topic cluster. So let's first look at how we get a relation learning module. So we adopt a pre-trained language model to learn a relation classifier with the user given parent-child pairs on the seed taxonomy. So for training samples, we generate relation statements from the corpus where a pair of parent-child nodes co-occur in a sentence in that corpus. And we assume that sentence implies their relation. So we train a pre-trained language model-based classifier to output whether a pair of nodes are of relevant relations or irrelevant relations. And then we first transfer the relation upwards to discover possible root nodes like lunch, food, and dish. This is because the root node would have more general context for us to find connections with potential new topics. And then we transfer the relation downwards from each internal node to discover more first layer topics and their subtopics. Since each candidate term has multiple mentions in the corpus, leading to multiple relation statements, we only count those confident predictions. And we judge by the majority of those predictions to find whether there is a relation between the new term and a candidate term on the existing taxonomy. And in the third step, we use a concept learning module to form a coherent topic cluster for each node. We will need to learn a discriminative embedding space so that each concept is surrounded by its representative terms, and we will use them to cluster and form a coherent subtopic nodes. We cannot directly use the unsupervised word embedding method because that might result in relevant but not distinctive terms. For example, the word food is relevant to both seafood and dessert. Therefore, we will need to leverage a weakly supervised text embedding framework to discriminate these concepts in the embedding space. And we will introduce these algorithms in the next part. But our main constraint is that the subtopics must belong to the representative words of that parent topic. Then also they must share parallel relations with the given seed taxonomy. So here we show some qualitative results of the generated taxonomies. So this is done on a scientific corpus. And the top one is the user given seed taxonomy, and the bottom one is part of our generated taxonomy output. As you can see, we can indeed find more topics under the computer science field and also more subtopics. And here is another example in the food domain where this is the user given seed taxonomy, and the bottom one is part of our generated complete taxonomy. And we also managed to find some meaningful foods and also the more fine-grained foods. So besides the taxonomy construction from scratch, recently there are also more and more needs for taxonomy expansion. This is because sometimes you already have a decent taxonomy built by experts and used in production. And most common terms are already covered in that taxonomy, but there are still new items incoming every day, and you cannot afford to rebuild the whole taxonomy frequently. So a reasonable way of doing taxonomy expansion or enrichment is to attach the new nodes into onto the existing nodes of a taxonomy. So there are three assumptions in taxonomy expansion. First, we assume each concept will have a texture name so that we can initialize the feature vector of each concept in the existing taxonomy. And secondly, we do not modify the existing taxonomy because modification of existing relationships can be risky and require high cautiousness. And thirdly, we focus on finding the parent nodes of each new incoming item. This is because new concepts parent nodes typically appear in the existing taxonomy. So we introduced TaxoExpand, which is published in WWW 2020. So there are basically two steps in solving this problem. The first step is self-supervised term extraction, which automatically extracts emerging terms from a target domain. The second one is a self-supervised term attachment. It uses a classifier to match a new node to its potential true parent and leverages heterogeneous sources of information, such as structures and semantic and lexical information. So we will mainly introduce the second step, the self-supervised term attachment step. So TaxoExpand uses a matching score for each query anchor pair to indicate how likely the anchor concept is the parent of query concept. And the key idea is that it represents the anchor concept or the parent candidate concept using the ego network. So here is an example of the ego network of the concept hospital room. And besides this ego network, we also add position information into this ego net. It shows which node is the grandparent node, which node is a parent node, and which nodes are the siblings. So after we combine these information together, we will train a graph neural network to output whether this candidate is a true parent node or not. And this training can be conducted self-supervisedly on the existing taxonomy. For example, we can randomly select a query node in the existing taxonomy, and we know it's true parent node. So the true position, we have the true position and its local subgraph. And we also sample some false position and their local subgraphs and use these created examples for training the graph neural network. And here are some case studies on the output of this TaxoExpand framework. Basically, for each query concept, it will predict a ranking list for the possible potential parent node on the existing taxonomy. For example, it outputs its predicted parent for archival science is library science, and its predicted parent node for Hindi language is linguistics. And also, we can see that this graph shows that the true parent of new items mostly falls into the first results in the top ranking results of TaxoExpand. So, which shows that this method is quite effective in expanding the original taxonomy. So this is for this part, and you can look into more details from our references. So yeah, I think maybe I think we're just on schedule. So maybe we will, I will answer your questions in the chat box, and according to the schedule, we'll have a 20-minute break, and maybe like after 20 minutes, we will start our third part of the tutorial. Thank you.
Yeah, yes, thank you, Jashin. So there are several questions from the box, I think from the chat box. So the first one said, in UC phrase, there's a CN classifier to decide whether it's a phrase or not. but you mentioned UC phrase is unsupervised. Correct me if I'm wrong. Then how do you get to the phrase or not phrase label?
Yes, so we have two modules in the UC phrase. And it is indeed a unsupervised one. And the first module is the silver label generation module, where we use the max frequent patterns to get the pseudo high quality phrases from documents. And for those pseudo phrases, we will treat them as silver labels. So they will be seen as the good ones for the CNN classifiers, and the other ones will be seen as the bad ones for the classifier. And this is how we train the CNN classifier.
Yeah, I can add a little comments on this. Essentially is this question set is completely unsupervised, but we are using pre-trained language model to some extent. It's sort of supervised by pre-trained language model to that extent, but the pre-trained language model itself is unsupervised. So should we, answer like this, then they probably can understand something they got together, actually getting better. If you think about it, the pre-trained language model, they do have the embedding. Some embedding actually, if you look at the graph, actually you probably can see those things stick together based on the pre-trained language model, right? Yeah. But anyway, the second one is that you mentioned that UC phrase predicted more phrases than wiki. I'm wondering whether UC phrase can have some false positives. Have you done some qualitative analysis on the fatal cases of UC phrase?
Yes, I believe there will be some false positives for the UC phrase, but notice that we only mine the core phrases within each single document. So we want to avoid the error propagation from a single document to multiple documents. So when we train the CNN classifier on multiple documents, it is quite like you have most of the phrases are true, but there can be false positives in single documents, but they might not affect that much of the whole data quality. So in this way, we can ensure that the CN classifier will not face a very noisy labeled data set. But yeah, we can look into the UC phrase paper for more details on their case studies on how well the silver labels are generated.
Yeah, actually, Jiaxin mentioned about you can go back into the research paper. The research paper does give you a lot of very good examples on case studies. The case study does not mean every phrase UC phrase mine is the best. However, you based on these studies, you actually can see the UC phrase comparing with the previous approach. You did get many very, very good results. That means both from the quantitative study and the case study, you can see the value of UC phrase. I think there's another question. I wonder if you can give some examples as quality phrase can be used in real world applications where n-grams are more broadly used in spite of the low efficiency. So you may give some examples in the real world, Jiaxin.
I think, so I'm not sure if this question is asking about the difference between quality phrases and traditional n-grams. Yeah, I think we have, so I think we mentioned that in traditional n-gram, in traditional NLP studies, if you want to extract quality n-grams, you are mostly based on a statistic method, and you want to find which. So based on frequencies or PMIs, you extract the quality n-grams, but sometimes you might ignore the infrequent but high quality phrases. So our goal is to both focus on the precision side and the recall side. We also want to get those infrequent ones, but are of high quality phrases.
Yeah, I can add a little on this comments. Actually, this quality phrase mining, our group actually generated quite a few already, including SEC phrase, auto phrase, UC phrase. UC phrase is most recently generated one at KDD last year. But if you go back to SEC phrase and auto phrase, these two previous quality phrase mining, these quality phrase mining has been used in many companies, including Google Research, Microsoft, and Facebook. Actually, one company, this SEC phrase actually published in 2015, just in the same year. Actually, it got, I think it's get award. Plus, I think I basically show you the which company. That's a travel company. Actually, they sent us their internal blog. They are using it. I also know a few companies' products, I probably should not say explicitly. It's very popular used in the social network analysis. The company, actually the person explicitly communicated with our group, said they are using our open source software. Okay, so you probably can see it's very popularly used already. Of course, not as many researchers they are still using n-grams, but the companies already pick up. So you probably can see it's very powerful. Okay. So the last question said, can RASTA and CoRare be applied to harder data sets such as biomedical literature and provide accurate results? Jiaxin, you, since this CoRare was developed by you, you'd very like to answer it.
Yes, yes. So both of these methods are they are domain independent or domain agnostic. So they can apply to more specific data sets like biomedical literatures. But if you want to achieve good results, I recommend you to replace the pre-trained language models in these these frameworks by the language models pre-trained on the in-domain corpus. That means you might want to use BioBERT or other BERT models that are already pre-trained on biomedical literatures, and then apply the similar frameworks. And I think that will provide much better results.
Okay. Yeah, I think we basically finished this. I probably don't want to extend too long. I believe we still should have, we originally said 20 minutes break. We probably still should have 20 minutes break. Is that good? Okay, so now is, I think it's 3:55. So we probably get a 4:20 Pacific time, then we'll come back. Is that good? Yeah, thank you. So there are some other questions probably we're not answered by you taking our time. We can answer this by just sending the scripts in the chat. Okay, thank you. We'll see you in 20 minutes. Thank you.
Hi, Yumeng and Professor Han. Shall we start now?
Yes, let's start now. Okay.
Sure.
So we will start our part 3. So Yu-John, so you just go ahead.
Sure. Yeah. Can you see my screen?
Yes.
Great. So hello, everyone. Let's proceed to part 3, embedding-driven topic discovery. And this part will be jointly presented by Yumeng, Jiaxing, and I. Each of us will roughly cover 1/3 of the content. So to give you a quick overview, in this part, we will cover 4 things. Unsupervised topic modeling, basically given a large corpus without any annotation, how to discover interesting topics from the corpus. And then we will cover supervised and seed-guided topic modeling. So by supervised, we mean that each document in the corpus has a topic label and how to use these labels to enhance the result of topic discovery. And by seed-guided, we mean that users are willing to give a small set of seeds for each topic and how to discover topics that are related to each of these seeds. And then we will discuss about discriminative topic mining, in which case we need to ensure that the topics are distinctive from each other. And finally, we will cover clustering-based topic discovery because we have discussed the power of context-free embeddings and contextualized language models. Can we directly cluster embeddings or pre-trained language model representations for topic discovery? So in the first 2 parts, we will mainly focus on earlier methods based on latent duration allocation. And in the last 2 parts, we will talk about how to use text embeddings and pre-trained language models inside. So yeah, to start with, what is the motivation of topic modeling? Let's imagine that we are given a large text corpus, for example, a collection of news. We need to effectively and efficiently digest this corpus. What could be the most efficient approach? Actually, knowing what important topics are inside could be a very good starting point. For example, given the word cloud here, you know that this corpus may be related to topics including pollution, internet, or education. Also, topic discovery facilitates various downstream applications, including document classification, document retrieval, and text summarization. So this is the motivation. And then how to discover topics automatically from the corpus. Because we first talk about earlier methods, so we assume we don't have tools like text embeddings or pre-trained language models. And then the most intuitive way is to model the corpus statistics. So let's first ask ourselves, what is a topic? Actually, from this perspective, each topic can be described by a probabilistic distribution over the words. For example, in the first topic here about biology, words like gene, DNA, or genetic could be top-ranked words or cover higher probabilities than other words. And also from this view, each document can be viewed as a probabilistic distribution over the topics. For example, this document 1 may have 23% on topic 1 and 33% on topic N. So this is the basic idea of latent duration allocation, or LDA. To give you one more example, here the news document is represented as a mixture of various topics. For example, 40% on politics, 50% on economics, and 10% on sports. Independent from this distribution, each topic is also viewed as a distribution over words. We show 2 examples here of the topics politics and sports. And in politics, you can see words like campaign or speech, they cover higher probabilities. And in the topic sports, you can see top weighted words like fan, baseball, or maybe football or basketball. Yeah. And here, duration priors are imposed to enforce sparse distributions. This is based on 2 intuitions. First, documents can cover only a small set of topics. It cannot be related to everything. And the second intuition is that topics can only use a small set of words frequently. So based on these two sparse intuitions, we use durational priors to enforce the distributions here. That's why the model is called latent durational allocation. And to interpret this sentence, you can think that durational priors are some distributions of distributions, and those sparse distributions, they are more likely to happen. Formally, LDA is a generative model which formulates the statistical relationship between words, documents, and latent topics. Using this process, the documents can be created in the following steps. First, for each document, we sample its topic distribution. You can imagine if there are 10 topics, then theta I is a 10-dimensional vector. And then for each topic, we generate its word distribution. So if the vocabulary size is 10,000, then 5K is a 10,000 dimensional vector. Then for each word position in the corpus, we first determine its topic. For example, this word, this position, it may be related to topic 1. Then we go to topic 1 because we already have its word distribution, and we sample a word. That's the final word displayed in this position in the corpus. So we can see lots of parameters here. These two distributions are the ones we would like to get finally, and also we have some latent factors. At the very beginning, we do not know any parameters here, so that's why we need to learn them from the corpus, and that's the model inference stage. Let's check what parameters need to be learned. So W is already observed because we have the corpus. Alpha and beta, they are hyperparameters, and they are usually provided by common practice. For example, for alpha, it is usually set as 50 divided by the number of topics, and beta is usually set as 0.01. So yeah, so all the remaining parameters, theta, phi, and z, these are three families of parameters. We need to learn them from the corpus using maximum likelihood estimation. So if you only care about topic discovery, that's the most important. That's the most important keywords for each category, for each topic. Then phi is the final result you are expecting. Okay. So due to the intractable posterior in the LDA model, it is complicated to infer all these variables 100% correctly. So there are some approximation methods, including Monte Carlo simulation, Gibbs sampling, and variational inference. So that's pretty much for unsupervised topic modeling. Now let's proceed to supervised and seed-guided topic modeling. First we would like to ask why we need these two settings. This is because LDA is completely unsupervised. It cannot take user supervision, which means it cannot reflect users' particular interests. We show an example here. There are 10 topics generated by LDA on the New York Times dataset. And you can see that there's no sports-related topic inside. So what if the user is specifically interested in sports? Then the results may not be an interesting result for this user. To give you another example, maybe we have a large collection of product reviews, and a user may care more about the product category related topics. For example, he may want books to be one topic and electronics to be another one. But without any supervision, LDA may generate something related to sentiments. For example, good as a topic and bad as another one. In this case, the dimension of the user's interest and the dimension of the LDA's results are not well aligned. So that's why we need to take user supervision into account. So there are mainly two types of models incorporating supervision. The first type is called supervised LDA. It uses document level annotations. For example, the users can annotate each product review in a corpus by its product label. Then the LDA model may know, okay, I would better generate topics related to the product category dimension instead of the sentiment dimension. So supervised LDA actually takes unsupervised LDA as the backbone, and it just adds a simple step at last, which is that After getting all the topics of each word positions, it used these latent topics to generate a label of the document, which follows a Gaussian distribution. And it is already observed because we have the labels of each document. However, in some cases, users cannot afford to provide so many annotations because he or she needs to annotate every document in the corpus. So to alleviate such annotation cost, there's another form of user supervision, several seed words for each topic. For example, the user may be interested in the sports topic, and then he may provide football, basketball, and baseball. That's all three seeds of this topic. And using these seeds, seeded LDA actually incorporate them in the following way. So when generating each word, the model has two choices. Choice one, it can generate the word from a regular topic, then it follows the routine of unsupervised LDA. The second choice, it can generate the word, sample the word from a seed topic, then that word must be from the seeds. For example, if the word is from the sports topic provided by the user, it must be football, basketball, or baseball. So this is the last step of this generation process. And also, seeded LDA proposed a group topic distribution to regularize, to bridge the connection between regular topics and seed topics, in which way it can be used to improve the learning of document topic distribution. So that's some basic introduction to the LDA-based models. And now we would like to introduce some new things. The first is discriminative topic mining. So still, we first ask, what is the motivation? So this question is related to what are the limitations of topic models. First, as we mentioned in previous slides, unsupervised LDA fails to incorporate a user guidance because they tend to retrieve the most general topics, may not be of a user's particular interest, and may provide a biased summarization. And even for seeded LDA or supervised LDA, they usually fail to enforce distinctiveness among retrieved topics because they do not explicitly impose discriminative constraints. However, from the user's perspective, when they provide some seeds or concepts, they wish such seeds to be most effectively interpreted by their uniquely defining features. For example, given two topics, Egypt and China, users may want pyramids under Egypt and Great Wall under China. So if you just find some common words like politics or economics under both topics, that's not a user-desired output. To give you another example, we have three topics retrieved by LDA from the New York Times corpus. We find it is difficult to clearly define the meaning of these three topics due to an overlap of their semantics. For example, you can see United States everywhere. Yeah. So what is the expected task in such requirements? So based on this, we define a new task called discriminative topic mining. That is, given a text corpus and a set of category names, we aim to retrieve a set of terms that exclusively belong to each category. For example, we have three categories: the United States, France, and Canada. It is correct to retrieve Ontario under Canada because it is a province in Canada. However, it is incorrect to retrieve North America under any of these categories because North America is more general than any of them and it does not belong to any countries. Also, it is incorrect to retrieve English because English is not a discriminative term belong to any of these categories. Yeah. So to summarize, the settings of discriminative topic mining is that it requires a set of user-provided category names and only focuses on retrieving terms belonging to the given categories. So from the supervision point of view, it is similar with seeded LDA, but we no longer output probability distributions. We just have retrieved terms for each topic. That's its first difference from topic model. And secondly, more importantly, it imposes strong discriminative requirements that each retrieved term under the corresponding category must belong to and only belong to the category semantically. And this will require the help from some modern tools like embedding and pre-trained language models. And then Yuman will cover the second part here. Yeah.
Thanks to you, John, for the introduction of the first subpart of our topic discovery section of the tutorial. So I will be introducing our two proposed methods for the discriminative topic mining task. The first is called Kate, and the second is called Josh. And the first one, both of them are on discriminative topic mining, and the first one is on flat cases, where we assume that all labels are parallel. And then the second Josh model assumes that there could be a latent hierarchical structure in the label space. So let's first get into the Kate method. The general motivation of combining the embedding learning and topic models, the idea of topic models is that they both have pros and cons. So the advantage of topic models is that they can discover hidden topic semantics by modeling the global co-occurrence statistics of words. But the drawback of topic models is that they cannot really model the word order information, which is essential for defining the semantics of the word, because they are following a bag of words generative assumption. And on the other hand, word embeddings also have pros and cons. The advantage of word embeddings is that they are able to capture the local context similarity. So basically, they do not assume that the words word information can be fully ignored. But the drawback of learning word embeddings for topic discovery is that the word embeddings usually do not exploit document level statistics or the global context, because they only assume that the words are correlated with their local context. And also, there are no topic related assumptions in word embedding learning. So basically, we cannot derive latent topics by only learning from word embeddings. And we aim to take advantage of both frameworks for the goal of topic mining. We have a three-step generative assumption in the Kate embedding framework. So basically, we assume that the users are able to provide us with a set of label names representing the N categories. And then we assume that each document in the corpus is correlated with one of the N categories. So this is to model the topic assignment of documents. And in the second step, we are assuming that each word in the document is generated conditioned on the semantics of the document. So this is to make sure that the word semantics is aligned to the global context of that document. And in the third step, we assume that the surrounding words of each word in the local context of is basically generated conditioned on the semantics of the center word, making sure that the local contexts are coherent with the center words. And then we will compute the likelihood of the corpus generation conditioned on this generative process assumed. So our objective will be optimizing the negative log likelihood of this conditioned corpus generation probability. So basically, we have three parts. In the first part, this probabilistic generation relationship is basically to model the topic assignment of each document, and then the second to model the global context, and the third to model the local context of words. So once we have this objective, we can train the word embedding model and topic embeddings on this target corpus. But there is one question: how do we know which words will belong to which category? Because this is needed in our objective. So as a starting point, we want to consider what kind of words can be satisfied as the representative words for each of these categories. we consider two aspects. The first aspect is called relatedness. So basically, we want to make sure that the retrieved terms are semantically correlated or relevant to the target category. And secondly, we want to consider also the specificity of the retrieved terms, because we want to make sure that the representative terms of a category should be semantically more specific than the category name. As an example, we can retrieve Ontario as the representative term for Canada because it is both related to Canada and more specific semantically than Canada. The next question then becomes, how can we know the specificity of words? So apart from learning the word embeddings, we define a new learning target called word distributional specificity. We assume that there is a non-negative scalar called kappa. And this kappa value is correlated with each word, indicating how specific the word meaning could be. And we assume that the value of this kappa scalar indicates the extent of the specificity of the word. So the bigger kappa is, the more specific the word meaning corresponding to that word has. So basically, if that word is very specific and fine-grained, we can expect it to be appearing in less varying contexts compared to very general terms. So for example, we will expect seafood, the word seafood, to be of higher word distributional specificity than the word food, because it's a specific type of food. So how do we learn these kind of specificity relationship in this embedding space model? We first introduced this VMF distribution, which we built our model upon. So this VMF distribution is a spherical distribution that characterizes how the data points are generated by a so-called spherical unit sphere distribution. So basically, there are two sets of parameters. The first one is the center direction of each distribution. And then there is a concentration parameter controlling how concentrated the data points are distributed around the center direction that are generated by this distribution. So our model exploits this VMF distribution to jointly learn the word embedding vectors, as well as the word distributional specificity. So in this figure below, we show for an example of the learning the embedding for food and seafood, and as well as their specificity. So if we consider a word food to be more general than the word seafood, then this general term food can co-occur with a wider range or a wider variety of different terms like salad, steak, seafood, and dessert. As a result, we can expect the data points that are relevant to food to be more separately distributed in this spherical space. In comparison, if we consider a more fine-grained or more specific term like seafood, then its relevant terms may be constrained to those terms that are relevant to seafood, like crab, fish, prawn, oyster, which are of a narrower range compared to those of the more general terms. As a result, we can expect these data points generated by the center word seafood to be more concentrated, and therefore we can expect a higher kappa value for this term. So once we can learn both the word embeddings and the word specificity values, we can derive this ranking measure to select the class representative terms. So first, we prefer words that are of high embedding cosine similarity with the category name. So this characterizes the relevance of the term to the category. And secondly, we prefer words with lower distributional specificity because they appear to be more general and easier to be interpreted. However, we must make sure that the term, although it could be less specific, it must be more specific than the category name so that it belongs to the category instead of the category name belongs to that term. So we conduct experiments on these two benchmark data sets and with two sets of label space. So the first New York Times data set has the topic label space and the location label space. And in the second Yelp review data set, we have the food type and the sentiment label space. We can see that our method Kate are able to generate or retrieve very concrete and also semantically relevant terms according to the given category name. So in this table, the first row, the words in the first row are the category names provided by the user, and this is the only supervision we need to obtain from the user. For example, when the user provides us with Britain and Canada, our method Kate is able to retrieve both distinctive and semantically relevant terms under these two categories. And we can also do a very good job on other like label space like topic, food, and sentiment. And also quantitatively, our method can outperform the previous topic models in terms of both topic coherence and the accuracy in terms of whether or not the term, the retrieved words belong to the desired category. And here is an illustration of the discriminative embedding space learning process. So at the beginning, the embedding space looks random, and with our more and more concrete and specific terms retrieved under each of the category, we are able to derive a very distinctive and discriminative embedding space so that our retrieved terms are the very representative and distinctive interpretations of the categories. And also we're able to conduct coarse-to-fine topic analysis by sorting these retrieved terms according to their kappa values or their specificity. So when we set a threshold to be lower, we can expect more general terms to be appearing in the top words. Whereas if we set the kappa value threshold to be larger, we can see that more concrete terms will appear. And next, we will introduce the hierarchical topic mining framework called JOSH. So the motivation of learning hierarchical representations for hierarchical topic mining is that sometimes we need to conduct coarse-to-fine topic understanding or hierarchical corpus summarization or hierarchical text classification. And these label space could be well organized into a hierarchical structure. So we aim to model the corpus generation process under this hierarchical topic structure. So at the beginning, we want to first clarify that we don't want to use the previously introduced hyperbolic models in the first section. So the major reason of not using these hyperbolic space models like Poincaré or Lawrence models is that these hyperbolic embeddings preserve the absolute tree distance, which means that if the two nodes have similar tree distance in this given label tree, then their embedding distance will be also similar in a hyperbolic space. So here is a simple example illustrating why we do not want to preserve the absolute tree distance instead of using it as a relative measure. So consider the tree distance between the two label sports and arts. Their tree distance is 2. And the tree distance between the baseball and soccer is also 2. But if we consider the semantic correlation between these two pairs, actually the category baseball and soccer are more similar than the pair sports and arts. So this is saying that we should not take the tree distance as the absolute measure when we want to do embedding over this label tree. So in this JOSH embedding method, we are doing a spherical embedding model, essentially jointly doing embedding of both the label tree and the text. So firstly, we want to make sure that the retrieved terms are very coherent to the target categories. So basically, we want to achieve this effect by pushing the representative terms of each category to be closer to the category representations in this spherical embedding space. So basically, we require every representative terms of this topic to be located within this green region. And secondly, we want to enforce that the different categories have different interpretations using words. So basically they have to be distinctive. And we accomplish this by requiring a semantic, by eliminating the semantic overlap between the retrieved terms across different topics. And also in terms of hierarchical topic mining, we want to make sure that we can, our embedding model can accurately reflect the hierarchical relationship within this given label tree. So basically we will recursively embed each local tree in this original label tree into the embedding space. So our model preserves the relative tree distance. So basically, if we consider each category, the tree distance between that category and its parent category would be 1. And the tree distance between that category and its sibling categories will be 2. So basically, we have to require the category to be closer in the embedding space to its parent category than to its sibling categories. And this is implemented by this margin loss by pushing the cosine similarity of between each category and its parent category to be over the cosine similarity between that category and any of its sibling categories over a margin. So once we have this embedding space correlations, we can derive this generative process condition on the given label tree. So in the first step, we are still doing topic assignment assumption. And the second step, still the global context generative assumption. And third step, characterizing the local context generation. And our Josh model is able to outperform the previous embedding methods, as well as the previously introduced flat topic mining method, Kate, on these two hierarchical topic mining data sets. So as an example, you can see that the user provided supervision are only the label names or the category names, which are indicated by the blue boxes. And then our model is able to retrieve these topic representative and distinctive terms under each of these given categories. And also we are able to do a good job on academic data sets like the archive data set. And here are some illustrations of how this vertical embedding space look like. So we can see that there is the root node is embedded in the center of this embedding space, and then there are tree structures reflected by this embedding space. And also we can see this is the archive data sets. We are able to embed the super topics as and those we are able to embed those subtopics to be surrounding those super topics, and those super topics to be surrounding this root node. Okay, so I believe the next part will be delivered by Jiaxin on how to leverage the pre-trained language models for clustering-based topic discovery.
Yeah, so thank you, Mo. I will cover this part, clustering-based topic discovery. So topics are essentially a group of coherent words. So it is natural for us to use some clustering-based algorithms and apply them on embedding space to get meaningful topics. So in this part, we'll talk about the clustering-based topic discovery. The traditional topic modeling frameworks use bag of words features, and they ignore the word ordering information. And in part 1 of the tutorial, we already introduced distributed text representations that better model sequential information in text. So can we take advantage of those advanced text representations for the topic discovery task as an alternative to topic modeling? So we want to combine word embedding and clustering. We want to cast topics as cluster of word types. This is similar to taking the top ranked words from each topic's distribution in topic modeling. And how to obtain word clusters? naively, we can run clustering algorithms on word embeddings. Since the text embedding space captures word semantic similarity, we can use distance-based clustering algorithms like k-means to cluster the similar words into the same group. And there are previous benchmark studies that apply common clustering algorithms like k-means or GMM to different types of embeddings, like context-free embeddings such as word-to-vec, GloV, fast text, spherical text embedding, and also contextualized embeddings such as ALMO and BERT. One thing to consider for using the text embedding is that the text embeddings do not explicitly encode the frequency information, but this frequency information is important for topic discovery. So there are two ways to incorporate frequency information. One is that we use weighted clustering. Basically, we can let the frequent words weigh more when computing the cluster centroids. The second way is to re-rank words in clusters by frequency when selecting the representative terms. So the previous studies used k-means or GMM as clustering algorithm and use spherical text embedding or BERT embedding as representations, and they lead to comparable results with LDA. So we want to develop more advanced clustering algorithms, and we also want to jointly modeling the document topic distribution with the topic word distribution while doing the clustering. So we want to introduce our framework top class topic discovery via latent space clustering of pre-trained language model representations, which will be published in WWW 2022. So our motivation is that the pre-trained language models have achieved enormous success in lots of tasks by capturing the long-range high-order semantic dependency, as well as the generic linguistic features. So given the strong representation power of the contextualized embeddings, it is natural for us to consider simply clustering them as an alternative to topic models. This is because topics are essentially interpreted via clusters of semantically coherent and meaningful words. And interestingly, such an attempt has not been reported successfully yet. So we visualize the embedding space of pre-trained embeddings on two corpus. And as you can see, they do not exhibit clearly separated clusters. If we directly apply k-means with a typical k, say k equals to 100, and it will lead to low quality and unstable clusters. The challenges are that theoretically such embedding space structure is contain too many clusters. The MLM pre-training objective of BERT actually assumes that the learned contextualized embeddings are generated from a Gaussian mixture model with the mixture components of the size of the whole vocabulary, of the number of the vocabulary size. So there is a mismatch between the number of clusters in the pre-trained LM embedding space and the number of topics to be discovered. If we use a smaller k in the clustering algorithm, then the resulting partition will not fit the original data distribution and will result in unstable and low quality clusters. And if we use a bigger k, then there will be many clusters and each cluster will contain only one unique term, which make the clustering result meaningless. So to resolve this issue, we propose to project the original word embedding space into a latent topic space with k latent topics. We assume that the latent topic space is lower dimensional and spherical with the following advantages. Firstly, the spherical latent space, as introduced in part 1 of this tutorial, it employs angular similarity between vectors and can capture word semantic correlations better than the Euclidean matrix. And secondly, the lower dimensional space can force the model to discard the information that is not helpful for forming topic clusters. So this is our proposed latent topic space, which is on a lower dimensional spherical space. And we propose a generative model for the joint learning, where a topic T is sampled from a uniform distribution over the K topics, and a latent embedding Z is generated from the VMF distribution associated with topic T. So this is our whole framework. Basically, we have this original embedding space of original embedding of word and document embeddings, and we use an autoencoder to project them into the latent topic spherical space and then reconstruct them to the recovered space. And the latent representation learning is guided by the clustering objective. So, and in the latent space, the clustering quality benefits from the well-separated structure of the latent space. So they can achieve a mutually enhanced effect. So we train this generative model by 3 objectives. The first one is to preserve the original PLM embeddings. And the second one is to is the topic reconstruction of documents to ensure that the learned latent topics are meaningful summaries of the documents. The third objective is a clustering loss, illustrated here, which enforces separable cluster structures in the latent space for distinctive topic learning. So we'll introduce the 3 objectives in detail. The first one is the preservation of original PLM embeddings. So we basically want to encourage the output of the autoencoder to recover the structure of the original word embedding space by minimizing the cosine distance between the original one and the reconstructed one. And the second objective is the topic reconstruction of documents. So we basically aim to reconstruct document semantics with topic representations so that the learned latent topics are meaningful summaries of the documents. So here we want to minimize the reconstruction loss between the reconstructed document embedding and the original document embedding. The reconstructed document embedding can be approximated by the weighted average of topic embeddings in the latent space, where the weights are correlated with the document topic distribution. And the original document embedding can be calculated by the average of original word embeddings in the document. And the third objective is to learn a distinctive cluster. Here we use an EM algorithm, which is analogous to k-means. The E step estimates a new cluster assignment of each word based on the current parameters. And the M step updates the model parameters given the cluster assignments. So in the E step, we use the current posterior to derive a new posterior as a new cluster assignment. Because we want to get distinctive topic clusters in the latent space, we apply a squaring then normalizing term on the current posterior distribution, which sharpens the topic word distribution towards its most confident cluster assignment. And on the denominator, we divide the term by a soft cluster frequency that encodes the uniform topic prior. And in the M step, we update the model parameters according to the new cluster assignment, so that both the topic center vectors and the latent representations are updated to fit the new estimate. So this is the joint learning of latent space mapping functions and cluster structures. And here we show some of the experiment results, both quantitative and qualitative ones. So as you can see, our top class method can achieve state-of-the-art on these quantitative evaluation metrics and outperform the previous methods like LDA and BERT topic. And for qualitative evaluation, we retrieve the top words for each topic, and top class can top class can find a meaningful and coherent words for each topic, but for previous methods, they can sometimes, so the baseline methods can generate some cross-topic or noisy words for some of the topics. We also provide a visualization of the latent embedding space during the course of top class training. So as you can see during the training, as the training goes on, the latent space gradually exhibits distinctive and balanced cluster structure. So to sum up, there are several advantages of top class over topic models. The top class, firstly, top class works with contextualized embeddings, which provide better word representation than the bag of words assumptions of topic models. And secondly, it employs pre-trained LMs to bring in general linguistic knowledge, which make the word representations more reliable and stable. And finally, top class does not involve any probabilistic approximations and is computationally and conceptually simpler than variational inference in topic models. So this is our introduction on this part. So I think, yeah, maybe we can go to the next part, which will be covered by Yu Zhang.
Okay, hello everyone. Now let's proceed to part 4, weekly supervised text classification, embeddings with less human effort. So still to give you a quick overview, we will first discuss the motivation and the definition, what weekly supervised text classification is and why it matters. And then we will discuss 3 major tasks: flat text classification with taxonomy information, and text classification with metadata information. For each specific task, we will cover some recent studies, either using text embedding or pre-trained language models. So let's start from the definition and motivation. The goal of text classification is that given a set of text units, they can be documents or sentences, and a set of categories, predefined categories, the task is to assign relevant categories to each text unit. You can see here that text classification has a lot of downstream applications, including sentiment analysis, location prediction, news topic classification, paper topic classification, email intent identification, and hate speech detection. So before we talk about the approaches to text classification, let's first discuss many different problem settings of text classification. We can divide the task along multiple directions. So in the first dimension, we can think text classification can be divided into single label settings and multi-label settings. In single label text classification, each document belongs to only one category. For example, if we want to do spam detection, given a new incoming email, it should be classified to either spam or non-spam. For multi-label text classification, each document has multiple relevant labels. This usually happens when the taxonomy, the label space is very fine-grained. For example, in Microsoft Academic, there are hundreds of thousands of different labels. And given the BERT paper, it is actually classified to about 10 labels here. You can say the paper is related to language model, name native recognition, question answering, sequence labeling, and so on. We can also divide text classification tasks into along another dimension, which is flat versus hierarchical. So in flat text classification, all labels are at the same granularity level. For example, if we want to do sentiment analysis of e-commerce reviews, we use the label space from 1 star to 5 stars, and it is a flat structure. In hierarchical text classification, labels are organized into a hierarchy representing their parent-child relationship. For example, We still do paper topic classification, but now we have the archive taxonomy. And you may know that the archive taxonomy actually is a 2-layer label hierarchy. In the first layer, there are coarse-grained labels like computer science, math, or physics. And given that the paper is related to CS, we can further classify it to like computation and language, computer vision, machine learning, and so on. Okay. So this is the definition of text classification. Then why do we need weakly supervised text classification? We know that supervised text classification models, for example, recent neural models like CNN, RNN, or Transformer, they rely on a significant number of manually labeled training documents to achieve good performance. However, in some domains, collecting such training data is usually expensive and time-consuming. And sometimes some new categories emerge. For example, given categories like different types of coronavirus, when the label is created, there's no any training data annotated. And in some domains, for example, scientific papers, annotations must be acquired from domain experts, which incurs additional cost. So in this case, users may not be able to label sufficient documents for training a deep neural classifier. Instead, they can provide a small amount of seed information, which are usually in 2 different formats. First, users can provide category names or category-related keywords. Second, users can provide a small number of labeled documents, maybe not 100 per category, but they can provide 3 or 5 per category. So this is the formal definition of weakly supervised text classification. We don't have massive human annotated training data, but we may have one of the following 2 weak supervision: keyword level supervision or document level supervision. So in keyword level supervision, as we mentioned, they correspond to sources 1 and 2 here. They are category names or keywords. So these 2 sources are similar because when you only have category names, you can think you have 1 keyword for each category, or you have a small set of labeled documents. And using these things, how to classify the remaining unannotated documents into predefined categories. So before we dive into the specific approaches, let's first talk about the general ideas in weakly supervised text classification. There are 3 general ideas. First is joint representation learning. Because the labels are usually described by words or documents, depending on what format of weak supervision we are using. So we can put all of these things, words, labels, and documents into the same space using embedding learning or pre-trained language models. Then if the document is embedded near a label, we may think, okay, this document should be classified to that label. Yeah. And second, we can do pseudo training data generation because we don't have enough label data. So the idea is to retrieve some unlabeled documents or synthesize some artificial documents using embeddings or contextualized representations. And then we give them pseudo labels to train a text classifier. Third, instead of relying on the local corpus, we transfer the knowledge of pre-trained language models to our specific classification tasks. So now I will show some specific examples or algorithms. Let's first talk about flat text classification. Okay. And here, the first work I would like to talk about is West class. It actually combines strategies 1 and 2 in the previous slides. So the idea is it can take both keyword level or document level supervision. The key idea is it first embeds all the words, including label names and keywords, into the same space. This is a spherical space here. And then it generates pseudo documents given a certain label. For example, given the category politics, we already know the words surrounding this category, and we can generate a sequence of words as a pseudo document. We assume this document is labeled as politics. And then we use all these pseudo documents to train a deep neural model. It can be CNN, RNN, a transformer, or even BERT, whatever. And after that, it also proposed a self-training step to you can think it is fine-tuning this model with some bootstrapping with some unlabeled documents with their predicted labels. To be more specific, during pseudo-document generation, imagine if we have category indicative keywords as supervision. We can use these keywords to fit a VMF distribution for each category. Okay, actually, in topic mining, we have discussed the VMF distribution. And what if we have category names as supervision? It can be transferred to the case that we have keywords, in which case we just need to find several words nearest to the category name as keywords. What if we have a few documents as supervision? In this case, we can retrieve words with high TF-IDF scores as our keywords. So in this case, we can learn a VMF distribution. That is, for each category, what is the word distribution? And using this distribution, we can sample from this distribution repeatedly to get a bag of keywords. And that's the pseudo document for this class. Yeah, and as I mentioned, there's a pre-training step, simply using pseudo documents to train the classifier, and then a self-training step, which is also covered in several of the previous algorithms. So actually, there are experiments on 3 data sets using different types of weak supervision, labels, keywords, or 5 labeled documents per class. And you can see that the West class outperforms other baselines, including fully supervised ones and semi-supervised ones, and topic modeling or traditional approaches by a large margin, especially when labels and keywords are used as supervision. And also, we plot the performance of different models with respect to different numbers of labeled documents per class. And you can find that when the supervision is very weak, for example, we only have 10 documents per class, actually the improvement of West class is larger. So in this case, it implies that pseudo document generation is more effective when the supervision is weaker. So one problem of West class is that it only uses context-free text embedding. And actually, pre-trained language model have been extensively used here. Because the reason of using pre-trained language model is that if we only use the local corpus, we fail to take advantage of the general knowledge source, for example, Wikipedia. Why do we need general knowledge? Imagine how humans classify text. Usually after seeing the many Wikipedia pages, we do not need any further samples. We can do classification with label names only. Okay, so that means there are some general knowledge contained in Wikipedia. And also, after reading the whole Wikipedia, those pre-trained language models have common linguistic features to understand text better, which can compensate for potential data scarcity of the local corpus. How to use such general knowledge, as we mentioned, neural language models pre-trained on large-scale corpora, they already learned semantic or syntactic features that can be transferred to classification tasks. Okay, so however, to use pre-trained language models here, we must first ask ourselves, what are pre-trained language models good at? Okay, are there any tasks context-free embeddings are not good at, but pre-trained language models are good at? First, it is very intuitive that pre-trained language models are good at disambiguation. So this inspires this work called Conwy. So the idea is as follows: user-provided seed words may be ambiguous. We give you an example here. We have 2 classes, soccer and law. And there's a seed word called penalty in soccer. However, let's check the following sentences. Messi scored the penalty. John was issued a death penalty. Okay, so of course, the first sentence belongs to the class soccer, but the second one, although there is a keyword matching penalty, but it actually belongs to the category law. This is because penalty is ambiguous here, and we need to disambiguate the senses based on contextualized representations. The idea is quite easy. We just, for each word, we find all of its occurrences in the input corpus. For example, so go may appear 100 times in the corpus, and we have 100 different contextualized vectors. And then we can run a clustering method, for example, k-means, to obtain clusters of different senses. In the original paper, they do not use k-means. They have some better algorithms to directly determine the number of clusters. So that's the extended form. We know, for example, go have two senses here. Penalty also have two senses here. But one sense of penalty is misclassified into the class soccer. So then an iterative process is proposed to adjust these keywords, in which case the one sense of penalty is adjusted to the law category. And based on the expanded and modified seed word list, we can use this word to match the original corpus. So if one document, one unannotated document can match multiple seed words here of the soccer class, then we know it probably belongs to the soccer class. So that's pseudo document generation. And we use these pseudo training documents to train a classifier to perform classification. Experiment results show that the full Conway model actually outperforms several variants. For example, if we don't use any contextualization, or we don't do seed expansion or seed adjustment, or we just replace BERT with a very simple word disambiguation algorithm called LASK algorithm, all these ablation versions will perform worse than the full model. And you can see that on some data sets, the performance of Conway is already very close to supervised hierarchical attention networks. Okay. So now let's think about what else can pre-trained language models do besides disambiguation. It is also good at predicting masked words, right? So that's the idea of the second work here. So because when we only have category names, we need to have more supervision, like what we need to generate more category indicative keywords. So the idea here is that, for example, we only have the category name sports. We mask it and let BERT to predict the masked words. BERT may think, okay, if we replace sports with baseball or handball or soccer, the sentence is still reasonable here. Then all these replaced keywords can be the augmented set of category indicative keywords. So yeah, so in this case, we have more supervision. And using these keywords, we can perform classification. Like given, essentially we use two different BERT models. The first BERT model is never fine-tuned, and we use it to generate the augmented keyword set. For example, given sports, we find baseball, handball, or soccer. The second one is fine-tuned for classification. Like when we mask the word sports, if we find that the replaced keywords have a large overlap with the augmented keyword set, we know, okay, this position is very topic indicative. And we use this sequence to train the BERT classifier, will improve its performance in classification. Yeah. So experiments results also show that on the 4 data sets, we use at most 3 words, actually 1 in most cases. We can outperform previous weakly supervised approaches significantly, including dataless and West class. And also it is comparable to state-of-the-art semi-supervised models like UDA. Yeah. Okay, so in the third study, we keep asking ourselves, what else can BERT do? It is good at predicting masked words or disambiguation. Is it good at, if we directly cluster the document representations, is it doable for classification? Actually, it is, because in this paper, ACL 2020 paper by Aroni and Goldberg, they show that an average of BERT representations of all tokens in a sentence or document preserves domain information well. For example, here you can see like a two-dimensional visualization of all the documents in the data set. And the 5 categories are well separated. So seems directly using BERT is a very strong tool for weakly supervised text classification. However, we have a problem here. Let's first talk about the simple idea. We just learned the representations for all the documents, and we set the number of clusters as the number of classes, and then we do clustering. We hope the clustering results are almost the same as the desired classification. However, this approach ignores the semantics of the label space, because the same corpus could be classified differently. Given the same NYT corpus, if we classify them along the topic dimension, or we classify them along the location dimension, we should get, of course, very different results, but their representations are the same, no matter you are doing topic classification or location classification, because the BERT model is pre-trained, the document representation is always the same. So this is the problem, and that's why Wang et al. Here proposed this X class framework. They want to get class-oriented BERT representations. To be specific, given the label space happy and sad, the representation of D1 should be different by if like the topic dimension, like sports, arts, and science are given. So for example, if happy and sad are given, D1 is embedded here. If sports, arts, and science are given, D1 is embedded here. So this is why so-called class-oriented representations. And based on this representation, they perform a document class alignment, and so the confident documents, which means their representations are near the original category name, can be used to train a text classifier. Okay. So the authors also perform experiments on multiple data sets where West class and Conway consume at least 3 seed words per class. Lot class and X class use category names only, and you can see in 5 out of 7 data sets, X class actually outperforms lot class. Okay, that's pretty much for flat text classification. Now we proceed to text classification with taxonomy information, or in short, hierarchical text classification. Okay, so there are 2 different types of hierarchical text classification. Let's first talk about the simple one, where the hierarchy has a tree structure, and each document is associated with one path, starting from the root node, maybe to a leaf or to an intermediate node. This is true. This is the case when you want to classify each archive paper to its main subject. Okay, and here still following West class or flat weakly supervised text classification, we can have 2 types of weak supervision. For keyword level weak supervision, we just have the name of each node in the taxonomy, or a few keywords for each leaf category. And for document level weak supervision, we can have a few labeled documents for each leaf category. So a wedge class can take both types of supervision. So yeah. The idea is quite simple because the labels of each paper must form a path from the root to a certain node. We can just build a local classifier per node. Like it takes all the documents classified to this node and then further classify it to one of its children. So this is essentially a flat classification task, and we can exactly follow West class in this case. However, in this case, we are not making full use of the taxonomy. So based on taxonomy, we need to have some further design. The first design is we build a global classifier per level. So at each level in the taxonomy, we construct a global classifier by ensembling all local classifiers. And then we use the unlabeled documents to bootstrap the global classifier. That's again, something like self-training. Okay. Yeah. And also, formally, like when we want to calculate the probability that the document belongs to a child category, it is the product of the document, the probability that the document belongs to the parent category times the conditional probability. This is given by the local classifier in the current layer. And similarly, as I mentioned, we can perform self-training. Still, you can see that actually WASH class outperforms different hierarchical methods. Some of them are fully supervised, some of them are semi-supervised or dataless. And then you can see that the performance gap is significant in most cases. Okay. So this is the simpler case of hierarchical text classification. Now let's consider a much complicated case. What if the taxonomy is directed as a cyclic graph? And moreover, each paper can have multiple categories distributed on different paths. It is no longer one path starting from the root, and it may be multiple paths or not even paths, like it's just some scattered points in the taxonomy. For example, here, the document, we know that it is related to natural language processing, NLP evaluation, and behavioral testing. Note that even if the document is related to a child category, it is not necessarily true that it is related to its parent category. This is the case in some real applications. For example, if you want to do mesh indexing of biomedical papers, usually if you check their annotation, they usually only annotate the most fine-grained labels of the document. Okay. Okay, so in this case, because we have talked about 3 different types of weak supervision. In this case, we want to argue that only category names are a proper setting for weak supervision. Why is this true? Because taxonomies for multi-label text classification are often very big. For example, the Amazon product catalog or the MASH taxonomy for medical papers, both of them have tens of thousands of categories. And the Microsoft academic taxonomy has hundreds of thousands of labels. In this case, it is impossible for users to provide even a small set of labeled documents or keywords for each category. For example, if you want 3 labeled documents for each label, there will be also tens of thousands or hundreds of thousands of labeled documents. That cannot be afforded. The users cannot afford to provide that annotation. Similarly for keywords. So the only supervision is they have a name when they are created, so you can use it as the supervision. And the name do not necessarily appear in the corpus because they may be manually created with some conjunctions or abbreviations. So So in this case, actually this Taxol class work leverages pre-trained language models to perform classification. Basically, they use BERT or Roberta fine-tuned on the natural language inference task. To be more specific, in the NLI task, there is a premise and a hypothesis, and BERT and Roberta are trained to distinguish whether, to decide whether the premise entails the hypothesis. And they can be directly used in classification. Like if you want to check whether this document is related to NLP evaluation, you use the original document as the premise, and you use the label, you put it into a template or a sentence like this paper is about. For example, this paper is about NLP evaluation. This is the hypothesis. If the premise entails the hypothesis very well, you know that, okay, this document should be confidently related to this class. For example, in this case, the score of the entailment is 0.9 according to Roberta NLI. Then, you know the confidence that the document is related to NLP evaluation is 0.9. So this is how we use the pre-trained language model. And now the problem becomes how to use the taxonomy. Actually, the relevance model here, for example, BERT NLI, is a cross-encoder model, which means you cannot pre-compute the representation of each document for each class. So you must concatenate them, feed it into the pre-trained language model to get a score. So imagine if you have M documents and N classes, and you want to calculate the relevance score between all of them. The complexity is M times N instead of M plus N. Okay. So in this case, taxonomy is used to shrink the label search space with top-down exploration. The idea is as follows. If at the top level, we enumerate all the children of computer science, and we find that theory is very irrelevant with this paper because the entitlement score is very low. And then we no longer search its children. In this case, taxonomy helps us filter out completely irrelevant classes. Okay. Yeah. And after that, we have some pseudo-label training data because according to Roberta Large, maybe document 1 after the top-down search, we know it is related to SVM rank or implicit feedback. And we use these pseudo-label training data to train a text matching network. At the left side, it is a document encoder, which means given a document, we use BERT or any other pre-trained language models to get its presentation. At the right side, we have a label encoder. Because we have the taxonomy, we can use a graph neural network to encode the graph structure, which means the representation of a node may depend on its parents and its children. You may have seen this in previous slides talking about taxonomy expansion. And finally, we calculate the similarity between these two representations. In this way, the classifier can be trained and can be used to find more classes of the documents. And you can see that TextClass actually outperforms the previous hierarchical method or semi-supervised method or zero-shot method by better model document class relevance and better leverage supervision signals from taxonomy and better capture domain-specific information from core classes. Okay, so last I would like to talk about text classification with metadata information. So first of all, what is metadata? Metadata is prevalent in many text sources. We show 3 examples here: GitHub repository, tweet, and Amazon review. So given a GitHub repository, we have its contributor information, and we know contributors should contribute to repositories with similar topics because each contributor has his or her expertise. And also GitHub repository have some tags. For example, the DCGN here, it is related to generative adversarial nets or deep learning or so. Yeah. And similarly, given tweet, we know it has the creator information and the hashtag information. Given an Amazon review, we have its user, the reviewer information and the product information. Given scientific papers, we have authors, venue, references, published year, and so on. So all these metadata are actually strong topic indicators. How to leverage these heterogeneous signals in the categorization process. So that's what we did in our previous study. Okay, so actually we divide metadata into 2 categories. One is global metadata, which causes the generation of documents. For example, user or author, they create the document. And the other type is local metadata. It describes the document. For example, tags or hashtags. In other words, we can say that the representation or the semantics of a document actually depends on the semantics of a user or an author. And the semantics of local metadata like tags actually depend on the semantics of the document. We can also say labels are global and words are local, but they are beyond our discussion of metadata. Here we provide a network view of corpus with metadata. And if we rewrite it as a generative story mentioned here, they look as follows. We first use global metadata and label to generate document semantics, and then using document to generate word semantics and also local metadata. So to illustrate this process, we use GitHub and Tweet as a specific example. In the first step, the embedding of the document is generated by according to its similarity with the user embedding and the label embedding in the embedding space. And then each word is generated according to its similarity with the document embedding. Okay, so similarly, you can write down those conditional probabilities using the softmax function for steps 3 and 4. And now the problem becomes how to use this underlying generative process. Actually, they can be used in 2 ways. First, we have an embedding learning module, in which where all the embedding vectors, here the user, label, document, tag, and word embeddings are parameters of this generative process. And we would like to learn the embedding vectors, all these parameters, through maximizing the likelihood of observing all text and metadata. And after that, we proceed to training data generation, where all these embeddings have been learned and given a new label. We generate document embedding, and then the word embedding, and then the tag embedding. And then we can have as many as pseudo label training data as we want. These 2 modules are exactly correspond to the strategies 1 and 2 mentioned at the very beginning. Okay, and we conduct experiments on different domains: GitHub, Amazon, and Twitter. We find that metadata is more helpful on smaller corpora, and actually, Metacat outperforms text classification methods, fully supervised text classification methods, or weakly supervised classification method without considering metadata, or some heterogeneous information network embedding approaches. And in particular, it outperforms BERT in the field shot setting. Okay. We can also extend metadata to, CAT to jointly model metadata and hierarchy. So here we are doing hierarchical text classification, but the simpler version, where the label of each document is just a path. How to incorporate metadata inside. The idea is also very simple. We just put the hierarchy into the generative process. You may have seen Josh in the previous part. So here we have 3 steps. In the first step, the embedding of each child label is determined by the embedding of its parent. And then given a leaf label and the metadata of each document, we generate document embedding. And then given the document embedding, we generate the word embedding. Still using this hierarchical generative process, we can do joint representation learning and hierarchical data augmentation. So this is very similar with what we did in Metacat. And also we can find that we still outperform hierarchical, like fully supervised classification method, or some flat metadata aware classification method, and some HR embedding approaches, hyperbolic embedding approaches, and pre-trained language models. Okay, and we also visualize the tree, the label embeddings, and we can see they form a very good tree structure in the embedding space. Okay, so the previous, like Metacat and HimeCat, they only use joint embedding approaches. So how to use pre-trained language models in metadata-aware text classification. This is the most recent work called Michael. Actually, we are proposing a metadata-induced contrastive learning framework here. So now we slightly change our setting. The input is, of course, a set of labels, but each label, besides its name, we also have its description. This is the case in Microsoft Academic and also on PubMed. Like for each mesh label, it has its canonical label name, some synonyms, and label description. Okay, and we also have a large set of unlabeled documents associated with metadata. For example, authors, venue, and references that can connect the documents together. And The output, the desired output is a multi-label text classifier. The label space could be very large here, for example, tens of thousands of labels. Given some new documents, the classifier can predict relevant labels for each document. So how to use pre-trained language models here? Imagine if we could have some label documents, then we have some relevant document label pairs, and we can use them to fine-tune the pre-trained language model. There are two basic architectures, biencoder or cross-encoder. In biencoder, we encode each document and each label. By each label, I mean we concatenate its name and description into a text sequence. We can think of it as a document describing this label. And then we calculate the cosine similarity of these two embeddings to get the score. Or we can concatenate the document and the label description and feed it into a BERT model. After that, we take the concatenated description of the representation of the concatenated sequence and feed it into a linear layer to calculate the final score. Okay. The problem is we do not have any label documents. So like given a document and a label, we don't know the score should be large or small. So in this case, we seek help from contrastive learning. So here we adopted the seminal work by Chen et al. They propose a simple framework for contrastive learning. So instead of training the model to know what is what, in which case we need relevant document label pairs, we train it to know what is similar with what. In that case, we only need similar document-to-document pairs. And if we know two documents are similar, we have another document, we calculate the similarity between the two positive document pairs, and we calculate the similarity between the one document and its negative partners. We know the first score should be larger than the second score. This is, using this objective, we can fine-tune the pre-trained language model. The problem becomes how to generate similar document-to-document pairs. Actually, because the original paper talks about visual representations, and there are some text-only approaches. Here we propose a new way to use metadata to define similar document-to-document pairs. Namely, if two documents share a common author, or they have a common citation or common reference, or they share one author and one venue, or they have two common citations, the user can provide, can define what are similar documents based on the metadata. And use these structures, we can generate document-document pairs from the unannotated training corpus. Of course, this method can be used in both biencoders or cross-encoders. Yeah, and we conduct experiments on two data sets, and we find that actually it consistently outperforms text-based contrastive learning method and other methods using label names only. It is competitive with the supervised state-of-the-art trained on 10,000 to 50,000 label documents. And you can see that this conclusion is generalizable because no matter what kind of metadata we are using, in most cases, we can outperform unfine-tuned CyBERT. Except some special cases, and we have deeper analysis in our paper. Okay, so that's pretty much for this part. I have a summarization table here, and these are the references. So that's pretty much for this part. Thank you.
Thanks, Yichan. I think we may get 2 minutes for anybody to ask any questions because we got a pretty long discussion without any question answering. Anybody has any questions? Yeah, so one person, Ravati, said, can you bring back to the summarization table again for the break and the questions? You may go back just 1 or 2 more slides. You can go, yes, there one more, yes, here. Yeah, this is a summarization of the previous introduction by Yichan on many those classification algorithms. So anybody would like to raise question? I think Ravati you raise this question. Do you have any questions you may want to speak out, or you just want to type in? Okay. Yeah, you say you just want to see it longer. Yeah,
Sure.
I think that's, we were, like we said, we are going to publish those slides, but in the meantime, we will publish the video recording as well. So if you want to know more, all those papers, the papers published in our group, majority of papers, as long as it's not collaborating with like an industry, like a Microsoft Research or something, the code and data we can all put available. I think the current, if you do GitHub to the first author, you are going to find their code, likely data set, as long as it is allowed. That means if it's collected by industry, the industry using some data is, it's their own company's data, they will not allow us to publish it. Otherwise, if just by university, we actually publish the code, including the source code. Okay. So I think that's this slides. We probably, because we have only 15 minutes left, we'll not have a break. I'm going to give the last session. Then we will be able to do the final. Okay, let me try to bring up the very final part. Okay. Let me get into the presentation mode. Okay. Can you see this part? I hope everybody can see it. If you cannot see it, just a shout out. I will then do the mode. Hopefully you can see well. Then our because we have 15 minutes left, we definitely don't want to go over time. So I will give you a brief introduction on what is advanced text mining application empowered by this pre-trained language model. Okay. The first thing is I should say the pre-trained language model has been introduced by Yumeng and Jiaxin, and actually their applications are soaked inside. We did a lot of discussion on the applications, including including the phrase mining, including the concept taxonomy, construction, and also including topic discovery. And we also discussed the text classification methods. All of these you can think about as the pre-trained language model application already. So here we are going to discuss just two more. Of course, there could be many more with limited time, and I believe we can actually have many more things. If you like to know, we may have some specific discussions or go back to the reference papers. So I'm going to discuss one is aspect-based sentiment analysis, one is text summarization, then I'll do a brief summary. Okay. So for aspect-based sentiment analysis, the general philosophy is this, okay. We got lots of documents which may contain reviews. For example, Yelp review, on the laptops, restaurants, hotels, all these things. Okay. If we want to know, instead of just to say this for this restaurant, or how many people give 5 stars or 1 star. Okay. What you want to see is the concrete aspect and sentiment analysis. Okay. Just give you an example here. For example, this is one opinion, reviews. They basically say Mermaid Inn is an overall good restaurant with really good seafood. What you can see is one thing is about food. So the aspect is of food. And the sentiment is good, okay, like a good seafood. This is very explicit. You can see it. However, there are many reviews. They may not even separate the aspect and sentiment, just like the second one. Say, eye pleasing with semi-private booth, place for a date. Okay, yeah, I think one thing is I probably did not get my video, my own video showed up. Let me see whether I showed it up. If not, I probably should make my video visible because it's not polite. I show it completely. Okay, let me try to do it again. Sorry about this. Let's do this. Share screen. Okay, so let's redo this one again. Okay, so the second one is you can see for this particular review, you cannot separate this one. If people read it, say this one is about a good ambience. The aspect is ambience, the sentiments is good. But actually you read through the whole thing, like a place for a date. People can sense it's a good ambience. However, there's no separate, say, ambience or sentiment. You probably see this is a very tricky thing. If you do not do joint sentiment analysis, you just cannot catch what is the aspect, what is the sentiment. Okay. The third one is very short, but it's also a similar thing. They say it's to die for. Okay. For the restaurant, say it's to die for actually means good food, but such a short one. If you just base on die, you probably say this is bad. Actually, it's not bad. It's a good food. Right? So you probably can see it's very tricky if you just want to separate aspect and sentiment, and also do not look at the whole thing to do analysis. Sometimes you get wrong results. Okay. So that means most previous studies actually dealing with those aspect extraction and sentiment polarity classification in the individual mode. But this study is trying to, jointly resolve those things. Let me still put it in full screen mode. Okay. So let's look at this sample review, see whether how we can do this. Okay, that means how we can get both aspects recognized, the opinion recognized. Okay, so what you probably see is a pretty tricky task, but if we do joint topic analysis, we will be able to solve this problem. Okay. The problem, actually, you can think in this way. You can think if you do just like a good versus bad, or one aspect versus the other, is marginal topics. Okay, that means you do a marginal conditional probability, a marginal probability analysis. However, if you do joint analysis, like in the center, like a yummy or something tasty, actually it means good food, or helpful, or means good service. So these are joint topics. You probably can see there are words, they are independent of aspects. It's a good or nice, it's this one. But they are also something, you get one word, it actually implies both aspect and sentiment. So what we need is whether we can extract those kind of things, it will help our joint topic analysis a lot. Okay. So this work actually was done by Jiaxin and others. Jiaxin and Yumeng, they did this work, but they just give the topic, they need a little break. So I will just represent them to do this presentation. Okay. What you can see here is we can do, you have aspect things related like ambience, you have sentiment related like this good or great. So the whole thing, you can do individual study, but you can do joint embedding. And joint embedding, you use neural network or any deep learning method, you probably will get a joint ones, which is much more powerful. Okay, that means we can first leverage the in-domain training corpus and use some user-given words. User-given words, in many cases, it could be separated one, like they give you ambience or environment, or they give you good or great. These things user easy to give, but they don't want to give too many, like including those joint ones. Okay, what we need to do is we use embedding-based prediction on the unlabeled data, leveraged by neural model pre-training and self-training on both things jointly. Okay, so you probably can see that means if you think we want to do good food using this topic distribution on both things, okay, what you need to think about is you can do marginal topic regularization like this, okay? But the word can be classified, like you just give me good and food. I can get it from the marginal topic analysis. I can get many things independent of food, again, many good words, or something related to food, or get food aspect words, okay? But these just initialization. This is not joint analysis yet, okay? So to do joint analysis, you need to actually embed this whole thing together. Simply says, when you compute this analysis, you are computing both probabilities, okay? One, you can see when you get this word as a condition, you are analyzing on both sentiment and aspect together, okay? Calculate their probability. So to form this joint topic regularization, so it basically is doing, embedding on both sides and compute the probability on both sides. With the limited time, I basically show you the results, the details, you can see the paper, but you can see these words like cozy, intimate, actually is really about a good ambience. Cramped or something like unbearable, actually is a bad ambience. You can dig out many words which actually are the jointly both on sentiment and aspects. Okay. Now you make your analysis much more powerful because not only you see the marginal distribution, but you also see the joint distribution. Okay. With this, of course, the details is you are using some deep learning methods, but we are not going to get into detail. But you see, actually, it's very powerful here, right? You see the performance from both aspect extraction, sentiment polarity, classification. Actually, this method comparing even with their independent analysis on the previous method, this one obviously is a winner. Okay. And if you do the visualization, you also can see good versus bad. You can think that this 0 to 3 is good, and 0 go down is bad. But you probably can see these mapping is very clearly. You get a joint one, you actually can put them down, or some good one, you can push them up. Visualization, clearly you can see the differences. There are many other case studies. We don't really have time to do that. You can enjoy the paper when you read it, okay? Another one, I probably have much less time. I'll just give you another interesting one called sum dots. Actually, this one from my group, Qi Zhu, who is also a PhD student. He did this one. The interesting thing is, how can you do multi-document summarization without anybody trained? Okay, but what you need is a large document to do classification already in a hierarchy. Okay, just thinking about it, this one is multiple reports about an Ethiopian airline crash. Okay, you want to do the summary. What do you really want to do? You want to do summary like you want to point out this one is different from the other air crash because essentially it's Boeing 737 MAX. This aircraft gets some software bugs or something caused this. If you look at those things, you will know it's different from the other air crash. But how could you get this automatically without anybody trained like human? Okay. The interesting thing is you're not thinking your set of documents is alone. Your documents actually in the taxonomy. Okay. Not only you're looking at your siblings, because this disaster, they all belong to disaster. You're looking at the siblings, but also you look at your own air crash collection of documents. That means we're not only looking for siblings, we're looking for twins. That means these are documents all on air crash. What's the difference? then you are going to get the aspects, Boeing 737 MAX or software error, not whether or not a human. Okay, so that's the one you can see. What we see is we are going to use surrounding documents. That means we have lots of documents. You identify siblings, identify twins. The words related to sibling is important. Words related to twin could be more important. Then you are going to identify them. You are going to get the nice summary automatically without anybody trained. Okay, I already ran out of time. I just give you a little thing. This is the Picasso's is another group's work. It's very interesting using generative model, self-supervised pre-training to do summarization. This is another one, actually it's just last year by a group in Europe. Okay, what they do is they take some keywords to guide the summarization process. A more interesting one, actually is from our group working together with Google Research. The interesting thing is this, okay, people got lots of articles, okay, but once Google want to summarize this news article, they want to summarize really, really short, like this, okay. You get so many things, you get every article, get something, even title is longer, but you want to group them, you want to summarize it like this, Raptors versus Bucks prediction, okay, or something like this. Or you just say Raps versus Bucks, okay? Or like here, you probably say putting, order like invasion to Ukraine or something, Ukraine crisis or invasion or something. You want to give only 2 or 3 words. Can you do this automatically? Actually, this is the one they did it. You probably can see. Actually, it's already partially released in a Google News. Because there are millions of documents. Every day there are so many, you cannot just think it. All this done by human. How can we do this? You probably can see. There's a pre-trained language model, play a very important role. Okay, I ran out of time. I basically give you can go back to read the article. It's a very nice article, I should say. And a very nice results as well. So basically we ran out of time, but what you can see is this. We basically say massive text corpus plus existing knowledge base using pre-trained language model, using very, very few human annotation or supervision, but we can do a lot of things. Many things already push out. As people can use it with very little human efforts. So I think it's a very promising direction to go. The pre-trained language model is very powerful. The unsupervised, weakly supervised, or self-supervised, or distantly supervised method actually is very powerful. Okay, so I should thank my PhD students. They did a really, really brilliant work. Not only they did a real work, you see their presentation are really brilliant. So hopefully you really enjoy this tutorial. There are so many things, but I think if you read their papers, you will find many, many more. You'll enjoy working in this direction or know more about what can be done using the pre-trained language model plus weak supervision. Okay, so I should thank all the supporters, including like Army Research Lab, NSF, DARPA, NIH, and many industry research collaborations. Okay, thank you. So I think I ran out of time, but I enjoy their presentation. Hopefully you enjoy it as well. Okay, so for the slides and for the video, we're going to upload on our website. You go down to our AAAI tutorial website, you will be able to download the most things you like. Thank you very much. So we ran out of time, we will not be able to take more questions, but feel free, you can send your questions to the speakers, is special to the first author. Actually, we selected 3 brilliant PhD students. They authored or lead many, many important papers in this tutorial. So hopefully you enjoy their work and you can communicate with them further. Thank you.
Yeah, thank you everyone for attending. And if you have any questions, feel free to contact us, email us, or whatever. Yeah, thank you, and hope you enjoy the remaining of this conference.
Yeah, thank you very much. So enjoy. Bye.